Today we're going to try some of the hardest linear algebra problems in my university. These problems are slightly more difficult than the other problems. These problems are proof-based and are there to distinguish those who really understand the problem. And we are going to attempt as many of them as we can. I may refer to the solutions every now and then, but the thought processes that I employ here are genuine, and you guys can even use it to do your own exams and hopefully solve these black magic questions. Now, the questions are in the link in the description below, but I will write out the question on screen so that everyone can watch and enjoy the show as we solve them one by one. Let's look at the first question. So the first question tells us this. We will let an denote a non-zero vector that belongs to the row space of an m by n matrix B. So in other words, this guy belongs to the row space of B, where B is an m by n matrix. We need to show, we claim, that the null space of B is a subset of a hyperplane. It's a subset of the hyperplane given by the equation a1x1 plus a2x2 all the way to a(n)xn equals to 0. So we want to show that the guy on the left side is a subset of the guy on the right side. So here's my attempt at doing that. We will need to take any item in the left side and show it belongs to the right side. So we'll pick any item, let's say x, inside the null space of B. And we don't really need to use arrows here. When we write out symbols, we understand what it means by vector and scalar. So take any x in the null space. Then that tells us that bx must equal to 0. At this point in time, it feels a bit vague. What exactly do we need to do? Well, one thing we do know is that we would like to show our goal. Well, we need to show that this x belongs to the hyperplane. So our goal, our hope, is to eventually show that if we take a1, an, and we multiply it by, we do it this way, x1, x2, all the way to xn, we're gonna get 0. And this goal seems a bit far-fetched at this point in time. So how do we sort of approach this? The first observation I have is that the ai row vector belongs to the row space of B. So since this guy belongs to the row space of B, we can actually even, let's flesh this out a little bit more clearly. Let's write B this way as a bunch of rows. This will be m rows because there's m over here. Correct. So since the a1 to an belongs to the row space, there exists constants such that we can write the row space, or rather we can write the row vector in terms of the row space. C1, B1, plus C2, B2, all the way to Cm, Bm. That's what it means for the vector to be in the row space. And at this point in time, it feels a bit, how do we sort of continue with this? This is where I'll have to sit down and consider my options. Well, I noticed this is interesting. This is actually going to be C1, C2, all the way to Cm, multiplied by B1 as a row, like this, B2 as a row, Bm as a row. That sort of works out if we were to sort of rewrite this multiplication in this way. And the beautiful thing about this expression here is now, in fact, this guy on the right side, that's the row, is actually this actually refers to B. So that tells me that a1 all the way to an of x1, let's give a little bit more space, to x1, x2, xn can be written as a1 to an times x. But the a1s to ans can be written as c1s to cm's with a b, and the x remains at an x. But we know that bx equals to 0. So this will simply be 0, and therefore the entire expression will simplify to 0, which is precisely what we wanted to show. So that is how we think about the problem. We try to use all the different pieces of information that we can in order to prove our result. It's definitely not a straightforward, algorithmic, straightforward kind of proof where you follow some steps and you get an answer. We definitely need to play around a little bit with the definitions. Let's look at the second question. Oops. Look at the second one. Let's look at the second question. And the second question here says this. We'll let B be an M by N matrix. And in this situation, we have M being smaller than N. We need to prove a certain result. So we're claiming that for any vector B, so for any vector B, this system has infinitely many least squares solution. And this raises an interesting point. Nowhere in this question we're saying that the system itself has infinitely many solutions. We are saying that the system itself has infinitely many least squares solution. So let's start. And a very powerful result that we have in linear algebra is that we can always get least square solutions. What does that mean? Well, let's recall the definition. We say that let's just put it this way. Bx equals to B. So let's do it this way. Let's fix B in Rm. We know that Bx equals to B has at least one least squares solution. Whoops. And what does that mean in terms of matrix equations? It means that if we were to apply B transpose on both sides, U would satisfy this equation. So we do know we have at least one least square solution, but then that raises a question. How do we get infinitely many least squares solutions? Well, the trick here is the fact that M is lesser than N. And that tells us that as far as a matrix is concerned, let's just illustrate B here. If we were to write B, we have M rows and N columns. And the number of rows, M, is smaller than N. And what that tells us is that we do know a system with infinitely many solutions exists. Now, when B is non-zero, then there's no guarantee. But we do know that in this situation, if Bx equals to 0, this system is a homogeneous linear system. It will have infinitely many solutions. And how does N bigger than M play into this? Well, since N is bigger than M, the nullity, the rank of B is at most M, which means that by the rank-nullity theorem, the nullity of B being N minus M has to be positive. And since the nullity is positive, we get infinitely many solutions because this system is simply the null space of B. The beautiful thing about that is that we can say so Bx equals 0 has infinitely many solutions. So we will say that we will let V be one of these solutions so that BV equals to 0. And the beautiful part is we'll get any multiple of V is gonna allow it to be 0. Of course, we can pull the scalar out. So we're gonna get infinitely many solutions here. And we can assume this is a non-zero vector. Once that is in the bag, then we can try to make some observations. If BV equals to 0, then if we take B transpose on both sides, we are still going to get 0. And this is really interesting because now we can combine these two pieces of information and the fact that V, this is true for V, but this is also true for, any multiple of V. Because we can pull out the T's, because the BT's and the B's are linear, we can pull out the T's, and this will still give us a 0. So the fact that we have U giving us some solutions and TV giving us 0, in a sense, the TV doesn't really add anything, in a sense, to BTB. And here's how we get Well, we needed to show that there are infinitely many solutions, least square solutions. So here's how we do it. We will consider u plus tv. And what will we consider? We'll consider this combination. If we take BTB transpose of u plus tv. Since the matrix multiplication is, well, the matrix transformation is linear, we can basically do splitting. And we can even pull the t out from the second term. But we do know that B transpose BU is simply B. We got this information from this part over here. And we do know that B transpose BV, because V is an element of the null space, right? BV equals 0, that B transpose BV is 0. So we get B plus T times 0, T times 0, anything times 0 is B. So what this tells us is that U plus TV is a least squares solution to Bx equals to B. But T can be any real number we wish. And therefore we get an infinite number of solutions. We get an infinite number of least square solutions. Because how many numbers do we have over here? We have an infinite number of vectors that can satisfy this equation. So the key insight over here arises from the fact that when we talk about BV equals to 0, or when we consider the homogeneous system, if the number of columns exceed the number of rows, we will get infinite number of solutions, and that helps us generate infinite number of solutions in the equation. Okay, next question. Let's consider this matrix. We are given that we're given a definition of positive definite. Let's write the definition here. So we're given a definition. So we will let S be an n by n matrix. We say that it is positive definite. Whoops. We say that it's positive definite precisely when for any non-zero vector x, let's do it this way, we will obtain x transpose as x being positive. So whenever x is non-zero, then this expression here is going to be positive. And we are required to prove that, so we make a claim that, okay, so we'll let A be symmetric matrix. I believe that we should include the fact that it's symmetric here. We'll let A be an n by n symmetric matrix, and we claim that A is positive definite precisely when all of its eigenvalues are strictly positive. That's our claim, and we need to try to prove this claim. We definitely will need to take advantage of the definition of a positive definite matrix. So, well, positive definite symmetric matrix. So this is a two-directional proof because there are two arrows over here. So let's prove in two directions. We'll go this way first. We will first suppose A is positive definite. Then what does that tell us? We need to show that all of its eigenvalues are positive. So we'll let lambda be an eigenvalue of A. So what does eigenvalue mean? That means A equals to lambda for some V on 0. And we need to somehow use the fact that there is the positive definiteness over here. Well, if A is symmetric, what can we derive? I think I see something here, right? We have the AV is equal to lambda V. So let's check this out. AV is lambda V. The question tells us that if A is symmetric and A is positive definite, then if we were to multiply this guy over here, the entire expression V transpose AV will be positive. On the right side, however, we're getting lambda v transpose v, and v transpose v can be interpreted as the dot product. Right? And some people might go one step further to interpret it as the norm of v squared. But since v is non-zero, the norm of v is also strictly positive. If the norm of v is strictly positive, then we have that lambda norm of v squared being bigger than 0. We can divide out by the norm of v 2 times and get lambda being bigger than 0 as required. So that's how we can show that if A is positive definite, then the eigenvalues must. Well, let's go the other direction. So now we need to suppose all eigenvalues of A are positive. We need to show that A is positive definite. But perhaps let's write out the definition of it, right? So and let's just recall that A is symmetric. We want to show that A is positive definite. So we need to show this result, right? We need to show that for any vector, if this is non-zero, then this item over here is strictly positive. So we are trying to prove this result. And at this point in time, it feels a bit tricky. So usually it requires a little bit of thought. This is where I would usually sit down to think about it. And part of me wants to try to use the symmetry of A. So this is the part where we'll have to slowly think about the question. The symmetry of A tells us that it's orthogonally diagonalizable. Right? That's what the symmetry of A tells us. And so part of me wants to use orthogonal diagonalization over here. Let me see if this is a feasible strategy. Let's try... Okay, let's try this. Yeah, let's try the orthogonal diagonalization approach. So, since A is symmetric, A is orthogonally diagonalizable. And what that tells us is that there exists an orthonormal matrix P, well, orthogonal matrix I mean, and a diagonal matrix, such that when we take P transpose dP, we'll get A. Part of me wants to use this property. I don't know if we actually need this result. Part of me thinks it is a little bit unnecessary over here. Let me observe this for a moment and think about it. Oh, okay. I don't think we need the full force of this result, but I do find that we might still find it somewhat useful. So let's not use this result, but we still want the orthogonal diagonalization. We still want that. What that means is there exists a basis, an orthogonal, in fact, orthonormal basis. So let's write it down. For Rn, such that for each of the VI's, AVI equals to lambda VI, lambda IVI. So let's write it this way. There exists an orthonormal basis, and there exist eigenvalues, lambda 1s all the way to lambda n's, with the property that AVI is equal to lambda IVI. Right, so that's the idea. And in some sense, we can reduce every single vector in Rn as a combination of these VI's. So let's do that. I think we are good to go. Fix any vector, and since we have an orthonormal basis such that it has this special eigenvalue property, we can write x equals to C. Let's write it this way, as a summation of CIVI's from 1 to n. And the reason why is because we have that this set here is a basis. That tells us that we can now try to plug it in and see what we get. So let's plug in, then x. Well, let's suppose x is non-zero, right? Because we need to show that if x is non-zero, then we get the property, so x non-zero. Then I mean, we could say that there is at least one CI that is non-zero, right? But we might use the argument later. So what do we have here? Let's plug in X transpose AX and see what happens. So first up, we are going to get, let's get some more space here. X transpose is going to be this summation, and I'm going to suppress the indices just for simplicity. Transpose A CIVIs. This is by substituting the expression X. And the beautiful thing about transposes is that transposes can be brought into the brackets. So we can write the inside as a summation of CIVI transpose. And since A is linear, we can push the A's into the summation. So we can push it into the summation and pull out the CI's even. Right, so maybe we'll do it one step at a time. So our goal is to hopefully show that this guy is up. We get it 0 is our goal. So what can we do here? Like what we were saying, let's push in the A's into the sums first. And because A is a matrix, therefore it's linear, we can pull out the constant. We recall that AVIs are all equal to lambda VIs, and of course all of these lambdas are positive by the hypothesis of the question. So let's rewrite all the AVIs with lambda I VI. And this looks really promising, except that it's really messy. Yeah. Okay, let's try to work out some magic and see what happens. I think we keep using I's. We should probably use different letters just to highlight what we're doing here. So let's write this as J's. And I guess because we have so many letters moving around, let's just put in the indices. So now that we've sort of clarified that expression, we can notice that the I's can be brought into the J's. There's no J's inside the I's, so we can sort of bring it into the summation involving the J's. We'll bracket it this way. Okay, I think we are on the right track. Once again, transposes are linear, and we can basically pull out the summation one more time. In fact, we can pull out the summation a few more times. There we go. So we can really do a lot of properties here because of the fact that we've got linear properties. It's very, very nice. And we have what we call a double summation. Double summations tend to be really difficult to work with. But we have to remember one important thing about the VIs, and the important, crucial, pertinent fact is that they are orthonormal. Now, what that tells us about orthonormals is this very important fact, that Vj.Vi, which can be written, by the way, as Vj transpose Vi, that's what we're going to be using at the moment, it's going to be 0 if j is not equal to I. In other words, every single vector in the orthonormal basis, because it is orthonormal, it's orthogonal, and therefore the dot product must be 0. But if j equals to I, then not only is the dot product going to be positive, because it's orthonormal, the norm of each vector is 1, therefore the dot product of the vector is the norm squared. Let me just write it down here. So the norm of each vector is 1, which means that if we were to take the dot product, we're going to get the norm squared, which is 1 squared, which is 1. So not only is it positive, we even know that it's 1. So that tells us that for any particular j you give me, the only term that remains inside this sum is going to be when I equals to j. So Vj Vi is going to be equal to 0 for I not equals to j, as we've discussed earlier on, and it's going to be equals to 1 for I equals to j, which means that every single term gets destroyed except the I equals to j term. So we are going to write it this way. Whoops. Yes, actually this is correct. We just need to keep the terms where we are getting where we're getting all the terms when I equals to j. That's the only thing that we need. So in this case, we're going to get I equals to j here. Lambda j. Well, yes, lambda j, because I equals to j. We can get vj transpose. And instead of vi, it's going to be vj. Now, furthermore, the vj's are going to be 1. It's going to be 1. So we're going to get the summation j equals to 1n of cj squareds lambda j. This alone may still be 0 if all of the cj's are 0. But we've seen earlier on that x is non-zero, which means that there exists some cj which is non-zero. And this tells us that, well, maybe let's use a different letter. Let's call it ck as non-zero, which means that ck squared will be positive. And since all of these terms here are positive, we are basically adding up more and more and more positive terms, not negative at most. It has to be more than or equal to ck squared lambda k. Because each of the terms, each of the constituent terms here are non-negative. So we are adding up non-negative terms, including the ck term. Now this guy is strictly positive and this guy is strictly positive. This entire expression must be strictly positive. And that is for our symmetric matrix. We have proven that for any symmetric matrix, we get that it is positive definite precisely when, or rather, we get its positive definite precisely when its eigenvalues are all positive and strictly positive, not just non-negative, but strictly positive. I think we can get an analogous result when the eigenvalues are non-negative. I think we can get something like this. Okay. The next question says this. We will let P go from Rn to Rn be a linear transformation. And we will let Pm denote M composition. So we'll let Pm represent P composed with P M times. We want to show, we claim there exists some integer, and in this case, we always assume that it's positive. Well, let's just write it out. Let's just spell this out. So there exists an integer that's positive with the property that the range of pk will be equal to the range of pk plus 1, will be equal to the range of pk plus 2, so on and so forth. Perhaps maybe we could recall what a range is. So a range of a transformation is precisely the collection of outputs. In this case, it's going to be px, where x is a vector. And let's go ahead to prove this claim. Well, we can first make an interesting observation, and that is the fact that we will always get a bunch of subsets. Let's just illustrate the point. We'll consider the vector v equals to pk plus 1 of u. We don't know what u this is, but we'll suppose that v is equal to pk plus 1 of u. That simplifies to pk of pu. And this is a vector. This is a vector. P of u is an Rn to Rn transformation, so the whole thing lies inside Rn. This guy is a vector, which means that it lies inside the range of pk. Now what I did here is that v equals to pk plus 1 u is another way of writing v in the range of pk plus 1. This will tell us that v is equal to pk plus 1 u for some vector u. That tells us that pk equals to, that equals to pk of pu, which lies inside the range of pk, because the whole thing is a vector. If you're getting pk of a vector, this whole thing lies inside the range of pk by definition of pk, range of pk. Now what that means is that we have shown that the range of p of k plus 1 will always be smaller or not bigger than the range of pk. And this argument works for any positive integer k. So we actually have proven that range of pk is always bigger or not smaller than the range of pk plus 1, which is not smaller than the range of pk plus 2, and so on and so forth. This will always be true. the question is a little bit more strict. They ask if you can find a k, and we want to find a k, such that it must be equal. So how do we even start? Where do we even try to find such a k? This is where we have the power of contradiction. Contradiction will allow us to simplify this argument, and we can rewrite this statement to mean, so let's rewrite our claim. We have this result. Let's rewrite our claim. There exists some k positive integer such that for any index larger than k, so say n bigger than k, the range of Pn plus 1 is actually equal to Pn, the range of Pn. Or rather, range of Pn will be equal to the range of Pn plus 1. So that is sort of the claim that we are making here. And how do we sort of start? Let's try to prove this by contradiction, because it's quite hard to work in this way. It's quite difficult to actually make sense. I think this n bigger than or equals to k. So we're going to prove it, and we're going to make an assumption. We will suppose for any k in positive integers, there exists some n that is bigger than or equals to k with the property that range of Pn, we know that it's definitely not smaller than r of Pn plus 1. I mean, this part here is definitely going to be true every single time. So in order for them to be not equal, like that, we have a strict inequality there. This is going to be our strategy. We're going to actually be pretty sneaky about this. And I have to say, this is the first time I'm thinking about this. I actually solved this wrongly the last time. So it's nice to be thinking about something a little bit more accurately, if you would. Now, the strategy is this. The strategy is that, well, so for k equals to 1, there exists some natural number, n1, bigger or equal to 1, such that the range of Pn1 is strictly bigger than the range of Pn1 plus 1. You might be seeing where I'm going with this with the n1s over here. And the trick here is to go one step further. So for the integer n1 plus 1, there exists an integer n2 bigger than or equal to n1 plus 1 with the property that range of Pn2 is strictly bigger than range of Pn2 plus 1. And we will note that because n2 is bigger than or equals to n1 plus 1, this has to be the smaller one. The smaller power has to be not smaller than the bigger power. So it has to be this situation. This has to be the situation. Okay, so I'm just going to put this at the side over here. We can repeat this n times, right? Repeat n times. Perhaps we shouldn't use the letter n. Let's use a different letter. Let's use the letter m, just so we can, let's use the letter m so that everything is a lot more clear. We already use n to be the Rn, so let's not do that. There we go. So we will repeat n times, and we're going to get the existing m1 strictly bigger than, strictly smaller than m2, because you notice that m2 is strictly bigger than, is not smaller than m1 plus 1, and therefore this is strictly bigger than m1. This tells us that m2 is bigger than m1, and if you repeat the process, m3 would be bigger than m2. You can repeat this a total of n times. I am tempted to go one more step further. So let's go to n plus 1 times. And I want to do this in reason. I have a reason for this. So we have this sequence of numbers such that the range of Pm1 will be strictly bigger than the range of Pm2, and we'll keep going. It just gets bigger and strictly bigger all the way to the range of Pmn, and it's strictly bigger than the range of Pmn plus 1. We do have this property. And what's going on here? The key idea is this, right? So let's start from the smallest set, right? So since Rpmn plus 1 is strictly smaller than R, P, M, N, that tells us that we can find a vector in the right-hand side that's not in the left-hand side. We can find that vector, right? There exists some V, we'll call this Vn, it will slowly trickle down later on. Inside the right-hand side, well, inside the left-hand side in this case, right-hand side, whichever, whoops. Inside the bigger guy, that is not inside the smaller guy. That's the case, but you can repeat the argument downward. So since Pmn is strictly smaller than R of Pmn minus 1, there exists a vector Vn minus 1 in R Pmn minus 1 that is not inside R of Pmn. So by repeating the process, we can slowly obtain n different vectors. Well, this will be M2 and M1. There exists V1. And I believe M1 is actually strictly bigger than K, right? M1 is strictly, let's see, M1 is strictly bigger than K. For K equals to 1, there exists, oh, M1 might be K. M1 might be K. So I'm thinking, should I go a bit further and maybe I will go all the way to n plus 2 times because we can repeat it multiple times. So let's do it one last time, right? There we go. And before doing all of that, let's just include this last one since R, M, n plus 2 is a strict subset of R, P, M, n plus 1. There exists a vector n plus 1 that lies inside R of P, M, n plus 1 that does not lie inside R, M, n plus 2. Alright, so now what that tells us is that we have a collection of vectors. We have a set of vectors V1 all the way to Vn and all the way to Vn plus 1. You might be wondering, why did we purposely go all the way to n plus 1? And the reason why is because we're working in the vector space Rn. We did Rn. So if we have n plus 1 vectors in Rn space, we must have that it's linearly dependent, right? So since n plus 1 is bigger than n, this set is linearly dependent. And if this set is linearly dependent, that tells us that there exists some non-zero CIs. There exists CI, well, C1, well, let's just say CI non-zero, and there exists constant C1 all the way to Cn, such that we can take the linear combination and it will be equal to 0. In fact, we're going to write it this way. We're going to sum up all the i's, all the j's that are not equal to I, and then we're going to put the Ci Vj over here. This is a linear combination of the n minus 1 vectors, and we get that is equal to 0 because of the linear dependence of the set. So we can now isolate Vj. So Vj is equal to, well, Ci Vj is going to be the negative of everything else. Well, Ci Vi, what am I saying? The Ci Vi. It's J Vj. And we can divide by the Ci because it's non-zero. So let's divide it out. And this tells us that the Ci's lie inside a certain space, right? It lies inside this collection. And the real question is, what are we going to do with it? So I'll need to think about it. We know that each Vj, well, we know that the Vj's lie inside, we notice that the Vj's will lie inside. Now let's look at our definition. The Vj's will each lie inside R, P, M, J, excluding R, P, M, J plus 1. So we're almost there in our contradiction, and we'll ponder over this right about now. let's maybe draw a picture. Maybe that might help. If this is R of Pmn plus 1, then this guy is going to be R of Pmn. This guy is going to be R of Pmn plus 1. So I'm trying to see if there's any contradiction that we can derive over here. Now we do know that the Vi will definitely lie in the bigger space. That's no question. And that's not really the most helpful thing over here. At this point in time, I will ask myself, what if I not used the question? That usually comes in handy. But we've used pretty much everything here. I think I have an idea. Because I noticed something interesting here. Okay, I think we have some idea. We have some idea over here on what how to go about it. Part of me is sort of, okay, let's just write down the idea and let's just see what. So my idea here is to sort of split the ji's up. Because we do know that the i's get larger and larger, then we do satisfy some properties. I don't check. But we do have that. Okay, let's see what happens if we were to split up the j's. Now j's can either be smaller than I or larger than I. And there's something a bit sneaky about this, the way we defined it, right? Because we defined Vn to be in here, but not in the smaller set. And we've defined Vn minus 1 to be in here, but not in the smaller set. So most likely we can do a bit of manipulation. Okay, I think we have some idea over here. Now, because each Vj lies inside this range, it will lie inside the bigger space, right? So in other words, it will lie inside R of Pmj. I think that's pretty straightforward. But most importantly, it's gonna lie inside Pmi if j is, well, bigger than I. Yeah, if j is bigger than I, then it's going to lie inside R of Pmi. So in other words, this whole thing, this whole expression here is going to lie inside of R Pm sub I. Okay, I think we are good to go. Now, what that tells us is that all of these items here, they should not lie inside R of Pm sub I. And the reason why is because for any I that is, well, any j that is smaller than I, we've defined essentially, if this is R of Pi, then any j that is bigger or smaller than RPI, any j that is smaller than I, the RPJ is going to be bigger than RPI. And the way we define the VJs is that the VJs would not even lie inside the RPI at all. So what that tells us is that we are going to get, this expression equals to minus 1 over Ci, summation j equals to 0, I equals to minus 1. All of these guys cannot lie inside Rmi. So this expression here is going to be equal to Vi plus Ci summation j equals to I plus 1 and Cjj. And by not equals, we mean non-zero, right? We mean non-zero. Now this entire expression lies inside R Pmi. Correct? That's this expression. But this expression, if there is some Cj that's non-zero, then this expression cannot lie inside an RPMI. So what part of me wants to sort of obtain a contradiction somehow from this result? Right? So somehow I want to obtain a contradiction. Oops. That's that. So what this tells us, I think we are good to go. I think there is something over here we can use, and I think that will be pretty interesting. Okay, so let's continue from here. We're almost there. So we have two cases to consider, right? We have two cases. If we have a Cj that's non-zero, then the right-hand side lies outside of R Pmi, but the left-hand side lies inside R of Pmi contradiction. But we do have a second case to consider. What happens if all Cj's are equal to 0? Then the left side is basically going to be equal to 0 vector, right? Then Vi plus Ci summation. I think I'm missing a division here. I think it's 1 plus Ci. This guy will be equal to the 0 vector. But if this equals to the 0 vector, then we can write it this way, right? We can write it as Vi plus summation of j equals to I plus 1 to the n of Cj Vj, well, over Ci, so just write it this way, Cj Ci equals to 0. And this tells me that the set Vi plus 1, Vj is linearly dependent. In fact, we don't even need to talk about linearly dependence here, because what do we have here? Here, all the j's are bigger, or rather, all the j's here are smaller than I, right? Okay. Perhaps we can describe it this way. Whoops. Let's describe it this way. So the summation equals to negative Vi is non-negative. It has to be non-negative, which means that there exists some Cj that is non-zero, right? Among the Ci's. There exists some, well, let's write it this way. There exists some j that is bigger than I. There's some natural number j where j is strictly bigger than I and smaller than n, such that Cj is non-zero. But the beautiful thing about this is that Vi cannot lie inside the space. It cannot actually lie inside this space. Because if we think about it, we have written this as Vi equals to summation of j equals to I plus 1 n negative Cj over Ci Vj. This lies inside the range of Pm sub j plus 1. Because it's bigger, right? It's actually bigger. So it lies inside the range R of Pmj plus 1. However, the way we define I, Vi lies inside the range of Pmi, m of I plus 1, so it's I plus 1, right? Mi excluding R Pmi plus 1, right? So let's recall that when we define all of these items, for example over here, the Vn plus 1 lies inside the n plus 1 space, but not in the smaller space. Not in the n plus 2 space. The Vn lies inside the Mn space, but not the Mn plus 1 space. The Vn minus 1 lies inside the Mn minus 1 space, but not in the Mn space. So if we were to repeat the same process, we'll notice that each of the Vj's, because j is bigger than 1, j is bigger than I plus 1, right, lie inside R of P Mi plus 1. However, just like before, when we defined Vi, we made sure it lied outside of the space. So on the one hand, we have Vi lying inside the space. On the other hand, we have Vi lying outside of the space. And these two actually give us a contradiction. We have a contradiction. So what did we contradict? We actually contradict the fact we assumed this statement to be true, which is the negation of the first statement. If you want to check out my video on negations, you can check out my video on predicate logic. And because the negation is true, the negation leads to a contradiction. This original statement has to be true. And that is how we do it. That was fun. That was actually quite interesting. I have not referred to the solutions. I don't intend to refer to the solutions. I intend to struggle through the problem and eventually try to solve it without the solutions. That's the best way approach. That's the best way to do it. And you get to even see me struggle through the problem, and I like that a lot because it's possible to do it. Whether you have time to do it in the exams, that remains to see. But that's how I took this question. Next question. Question 5. We will let A and B be two diagonalizable 3x3 matrices. And they both have exactly two eigenvalues. we need to show, or rather we need to suppose, right? Suppose that A plus B does not have eigenvalues plus minus 2, plus or minus 2. And we need to show that A plus B is singular. So we claim that A plus B is singular. Now, if the claim is A plus B being singular and we are looking at the context of diagonalization, that really makes me wonder about eigenvalues and eigenvectors, right? In fact, we know that A and B have to be invertible. The reason why is because they don't have 0 as an eigenvalue. So we are going to try to prove this by showing that 0 is an eigenvalue of A plus B. We want to show this, or at least that's sort of the immediate go-to idea. When I say this question, I don't actually know how to go about it right away. So let's try to work it out and see what we can get. So let's see. If A plus B is singular, we would like 0 to be an eigenvalue of A plus B. Now, we know that A and B are diagonalizable matrices. So we'll write this way. Since A is diagonalizable, we'll just abbreviate that. We have a basis for Rn, right? There exists a basis of Rn with the property that AVI will be equal to lambda VI, where lambda is either plus or minus 1. We don't know which. And in fact, it's R3 because we're looking at 3 by 3 matrices. So we will say there exists this guy, basis of R3. And the same argument works because B is also diagonalizable. Perhaps we'll use the vectors U1, U2, and U3. Where BVIs is equal to mu VIs, mu's are plus 1. And this is where we need to start doing a little bit of work. Somehow we have to use the assumption that A plus B does not have eigenvalues plus minus 2. Now we'll get there. We'll get there eventually. But we'll have to consider some options. We have to consider our options. So we have that eigenvalues of A and B are 1 and minus 1. So we can suppose, without loss of generality, we know that A has eigenvalue 1. We don't know which vector, V1, V2, or V3. Let's just assume V1 is the one, and again, there are two situations for A. Either we have two eigenvectors with eigenvalue 1, or one eigenvector with eigenvalue 1. So let's just work out the cases and see what we get. So suppose, let's do it this way. Suppose, without loss of generality, that AV1 equals to V1, AV2 equals to negative of V2, and we'll similarly suppose likewise for BV1 equals to B1, U1, BU2 equals to U2. I'm negative, so what am I doing? And at this point in time, we have a few cases to consider, right? We actually do not know what happens to AV3 and BV3. So we want to split up the cases and see what happens. Let's consider each of these cases. I believe this will give us some insight. So AV3 equals to V3, or, well, not or, and BV3 equals to V3. This is the situation when both of the vectors, both of the eigenvectors have eigenvalue 1. And we can likewise write out the other situations. And we'll show that these cases either get us what we want or we get a contradiction. So let's look at the first situation. Now, once we have the first situation, part of me thinks I know what we need to do here. Now we can consider A plus B V3 because we can add the matrix, we can add the vectors on both sides, right? We can basically add the two equations. That's what we're doing here. But that gives us 2V3. And that means 2 is an eigenvalue of A plus B, which is a contradiction. And in fact, most likely case 4, because the negative signs are the same, are probably going to give us that property. In fact, I believe that is basically the question I think this is basically to the question. So this will be AV3. We're going to add the two equations once again. We're going to get 2V3, negative 2V3, which means that negative 2 is an eigenvalue of A plus B, which is contradiction. And in the center, if we add up the two equations, I think we're good to go. So a plus b v3, v3 minus v3 again gets 0. Therefore, 0 is an eigenvalue a plus b. And likewise, for the third case, if we were to add these two equations, then the negative v3 will add with the positive v3, we're going to get 0. And we're good to go, because this is basically the conclusion that we were looking for, which tells us that a plus b must be singular. And there is that. Alright. I believe the last time I tried this question, I used a rather convoluted solution to this. This feels really clear as far as I'm concerned. It's very clean. I like it a lot. Alright, question 6. We need to show, so we claim that every invertible matrix can be decomposed into A equals to BC. Okay, so we claim, so let A be an invertible matrix. We claim that every invertible matrix A can be decomposed. So in other words, there exists B and C and there exists an orthogonal matrix B. Let's write it this way. And there exists a upper triangular matrix C such that A equals to BC. So this is the claim, this is the question. We are asked to show that if A is an invertible matrix, we can find an orthogonal matrix and an upper triangular matrix such that A equals to BC. Now, from the onset, I have zero clue on how to do this. Let me just be flat out honest here. I have genuinely no idea how we are going to approach this. I think I have some ideas, but as a whole, I really don't know how to approach this. So, not sure how to even think about it. So this is where I need to sort of consider some options. Orthogonal and upper triangular. Okay, so I'm going to experiment first before solving this question. So B is going to be an orthogonal matrix. So we know that we want these things to be orthogonal vectors. And C is going to be upper triangular. It's going to look a little bit like this. This is going to be something. Over here is organism. Everything else at the top, we don't know. We don't know what these are. Okay. So if we were to do the matrix multiplication, let's maybe add some letters over here. Okay, so this will be B, right? B multiplied by C. Sorry, BC. And we're gonna maybe put some numbers here. This will be C11, C12. The convention is row followed by column. C22, C1n, C2n, Cn. Okay, we do not know whether the Ci's and whatnot are. We don't know whether they're zero. We only know the bottom parts. So, if we do the matrix multiplication, we are going to get C11v1 plus, well, not plus. That will be the first column. The first column is going to be C11v1. The second column is going to be C12v1 plus C22v2. Add a bit more space. So this is just the idea. I'm not proving anything yet, but this might give us some idea. And then the third column is going to be C13v1 plus C23v2 plus C33v3. And in fact, the last column is going to be the summation of Cin. So we'll let it be size n without loss of generality. Vi from I equals to 1 to n. That is actually going to be the nth column. This is going to be the nth column of BC. And what we claim is that somehow this will be equal to A. Right? We haven't proved anything yet. So in fact, I shouldn't really call this a proof. This should be more of an idea. We're just thinking of the problem. We want A to be equal to all of this. And what rings in my mind here is the fact that, wait a minute, A is invertible. So its columns forms a basis. Okay, so let's write it down. So let's write it this way. Okay, so since this might be a proof, I guess, since A is invertible, and we'll let A, okay, so let's do it this way. So we'll represent A through columns, right? Let A equals to A1, A2, AN. And the idea here is to sort of, we want A1 to eventually become C1, V1. We want A2 to be eventually C1 to C2 to V2. And eventually we want AN to be this guy. So that's the sort of idea that we're with. Now, since A is invertible, these columns form a basis. And if these columns form a basis, I remember there was a process that we learned in linear algebra where we can build the base up one step at a time. And I believe that's called the Gram-Schmidt process. So it's interesting because the Gram-Schmidt process tells us a bunch of things. The first thing is that, yes, you do get an orthogonal basis, but here's something really interesting in the Gram-Schmidt process. So we can apply the Gram-Schmidt process. And let me illustrate what's the interesting thing that happens. It just came to me, right? So how do we apply the Gram-Schmidt process? We're basically turning this set into an orthogonal set, right? So we're trying to turn this set into an orthogonal set. How do we do that? We will first define W1 to be, well, in this case, we can actually let V1 be the one. Well, W1. W1 is going to be equal to the first vector. W2 is going to be the second vector minus away the projection of the first vector. Now, the beautiful thing about this result is that A1 is equal to W1, A2 is equal to some constants, and in particular, this constant, times W1 plus W2. And W3 is going to be A3 minus something in terms of W1 minus something in terms of W2, which means that A3 is going to be something in terms of W1 plus something in terms of W2 plus something in terms of W3. And we don't have to concern ourselves with the details of the proof. The point is that we can write A3 as a sum of the Wi's. We know that the Wi's are going to be orthogonal. So when we apply the Gram-Schmidt process, we can obtain, this is just a side note, there exists an orthogonal basis for Rn, right? Let's put it over here, with the property that each AI is equal to the summation of, is a linear combination of the Wj's, let's do it this way, let's do Cij, j equals to 1 all the way to I. Each AI, as we can see here, is going to be a sum of Wj's where the j's are smaller than I, right? So A3 is a sum of W1, W2, W3, A2 is a sum of W1, W2, and so on and so forth. This captures this idea where we are adding up all of the Wj's where the j is smaller than or equals to I. And something interesting happens here because if we think about it, this form over here looks almost identical. If we think about it, that looks pretty clean. It looks about right, actually. So let's write it down, right? So we have this property, right? And how can we define it? Well, the Cij's here should be the column of the well, let's take a look. The Cij's here, right? It should be the columns, right? So I think we might need to do a bit of transposing just to be able to make the case. Of course, by the way, if Wi's are orthogonal, then we need to make sure that this guy is orthonormal. So we can apply the Gram-Schmidt process with this property, then we can normalize the Wi's. Then normalizing the Wi's, we get an orthonormal basis. Say we've used W, well, we haven't used, oh, we can use V, right? We get orthonormal basis V1 Vn of Rn, again with that special property, with the property that each AI is equal to the summation of dij's. Actually, why do we put dij's? I mean, the fact that we wrote ij actually is a bit arbitrary. We could have done ji and nothing would have changed. So let's change the ji's, right? That was a rather arbitrary choice there. But the beautiful thing about this approach is that now we are going to get the formula that literally repeats in the initial thought process of the proof. So how do we go about it? We will define, here's how we're going to do it. We're going to define, this is actually VJ, sorry. So we will define the orthogonal matrix B to be each column is basically a VI. And DJI is basically playing the same role as CJI in this question. So we can define the upper triangular matrix. Call it a letter C. It's called C, right? Yeah, C. C to be kind of weird that we're using these, but it's fine. It's not a problem. This is gonna be D11, D22, D12, all the way to D1n, D2n, Dnn. I go down this way. And everything else is gonna be a 0 because this is an upper triangular matrix. Usually the way to just show it is just a big fat 0 in the middle. It's fine. And we can check that this really does give us the result. Then, A being the columns A1 all the way to AN, we can actually verify to be each AI, or rather, let's multiply B and C together. Then BC can be calculated as V1, V2, Vn. This way. Multiplied by D11, D12 all the way to D1n, D22 all the way to D2n, Dnn, zeros. So we can write the first guy as D1V1, the second guy as D12V2 plus D22V2, the final guy to be the summation, I equals to 1 all the way to n of DINVI. Yeah, that's calculation. 1 to V1. There we go. And as we've calculated earlier on, this is actually precisely, if we sub in I equals to n, we're going to basically get the same formula. We're going to get all of the columns. And we are done. We know that the VIs all exist because of the Gram-Schmidt process, and we know that the DIs exist because the Gram-Schmidt process tells us that the AIs can be written in terms of the VIs. That's how we get our DJIs. We're good to go. And that's that. Well, that was rather complicated. Okay. That is question 6. And I have 21 questions. So we'll finish one more question and we'll go for a break. Not sure how many I'm gonna film. Actually, I need to go for dinner now. But I'll probably want to film this when I'm back. And we'll see how to stitch all the videos together. So we'll end off with one more question. And then we can go for our dinner. Right? So let's go for our next question. We have a square matrix of order n. And it has a property that A squared is equal to A. We first claim that A is diagonalizable. That's our first claim. And the second claim, this is claim number 2. I guess we can call this claim number 1, claim number 2. Is that the rank of A is equal to the trace of A. I remember the first time I solved this, I really had no idea how to solve this. I did take a look at the solutions. I did try to Google some stuff. And yeah, claim 2 is, I wouldn't say I would be able to do it in the exam, honestly speaking. There was a very interesting hack that we could use from claim 2. We'll take a look at it. So let's look at claim 1. A is diagonalizable. So how do we go about this? Interesting observation. Now, some of you might know about orthogonal projections and whatnot. Let's assume we know none of that. We could try to prove this. So let's think about how to go about this. Okay, I think I have some idea on how. This is a very sneaky property of matrices. There are a lot of things. So one of the observations that I have is the fact that if we take a squared of v, on the one hand, a squared of v is equal to av cos a squared equals to a. On the other hand, we can write this as a of av. And that tells us that av is an eigenvector of a with eigenvalue 1. So that's a rather strange result, I have to say. It's actually rather strange. So not too sure how to make sense of that. We'll definitely need to ponder on this. So that's AV is an eigenvector of A with eigenvalue. Because what that tells us is that this is true for any V, right? And then this is true for any V. So this actually tells us that for any V, AV is an eigenvector of A. That rings a bell with the idea of column space. Right? So therefore, the column space of A is a subspace of the eigenspace E1. So that's that. So that's rather suspicious. Part of me thinks something is going on here. So what about the nullity of A? Right? What about the nullity of A? Part of me is really suspicious here. Because if we think about it, AV equals to 0. So let's put it this way. For any V in Rn, or rather for any V in the null space of A, right, AV equals to 0. But that means AV equals to 0 times V. That means that V is in the eigenspace associated with lambdas with eigenvalue 0, and therefore the null space of A is a subset of the eigenspace with eigenvalue 0. And that tells me that the rank of A is less than the dimension of E1, and this tells me that the nullity of A is less than the dimension of E0. Now we know that in this context, the dimensions can basically add, but we can formalize it this way. So we'll write E1 to be this will be VK, let's call it VK, let this set be a basis for E1, and we'll I guess we can define, let U1 to UL be a basis for E0. Then the dimension of the total, the dimension of all of the eigenvalues, right? The dimension of, so we'll just say it this way, right? Right. So these are all of the. So then, A has K plus L eigenvectors, and because they're different eigenvalues, they must be linearly independent. On the other hand, the dimension of E1, as we've discussed just now, is bigger than or equal to rank A. So that means that dimension of E1 is the number of vectors in the basis of E1, so that's K. Alright, so maybe we can write it this way. So then, dimension of E1 is bigger than or equal to rank of A, but dimension of E1 is K, and L is the dimension of E2, which is bigger than the nullity of A. And every time I think of rank-nullity theorem, without any doubt, that's the go-to result whenever we think of ranks and nullities. So this tells us that then K plus L is going to be bigger than the sum on the right-hand side. But by the rank-nullity theorem, we have n vectors. So K plus L is at least n vectors. But on the other hand, the K plus L eigenvectors has to be linearly independent, which means that K plus L in Rn space can be at most n. Because if it's more than n, they'll be linearly dependent. So it has to be smaller than or equals to n, and it has to be at least n by the rank-nullity theorem. So in order for these two results to be true at the same time, we can only have one conclusion. The K plus L must be equal to n. But if k plus l equals to n, that means A has, well, k plus L linearly independent eigenvectors. But if A has n linearly independent eigenvectors, we can conclude that A is diagonalizable. Alright, that's the way to go. And finally, and this one I had to search it up the last time I went this, and I sort of remember the solution, so it's kind of unfair. We claim that the rank of A is equal to the trace of A. Again, I have to have full disclosure here. I believe I looked up the solution to this the last time around. So what we're going to do is this. We have the eigenvectors over here, right? And of course, I'll sort of quickly recap what is trace in a moment. We have these eigenvectors over here. So let's go ahead and prove the claim. I should prove this claim actually. Claim 2. So since A is diagonalizable, we have the vectors, right? We have the k vectors and the l vectors. So since A is diagonalizable, there exists a matrix P, an invertible matrix P, and a diagonal matrix D, such that P inverse AP is equal to D. So we still do have that property. What will P be in this context? I'm going to write it as V1s all the way to VKs, because we have V1 to VK as the basis for E1, and U1 all the way to UL over here. And D is going to be 1s for the first K columns, right? It's going to be 1s, and 0s for the remaining L spaces. Which makes sense, right? Because for the VKs, or for the VIs, each eigenvalue is 1. And for the UJs, each eigenvalue is 0. So we get this expression here. So we get P inverse AP equals to D, which means that, well, A is equal to P inverse. So this is the part where I just had to refer to the notes for this one. Not in this attempt, but prior to sort of doing this recording. Rank of A is going to be rank of, or rather, the trace of A, the trace of A is going to be the trace of PD P+. And something very sneaky about tracers is that tracers allow swapping of matrices inside. As long as the matrix multiplication makes sense, you can swap it within the trace. It's not an obvious result at all, but it can be done. And we can get a trace of the diagonal matrix here. Now, what is the trace of the diagonal matrix? Well, what is the trace of a matrix? So if you have a matrix, if you have a matrix M, the trace is the sum of the diagonal terms. You're going to add up the diagonal terms. So if we calculate the trace of D, we're going to add up the diagonal terms. But in this case, there are only k terms. There are only k terms here, which are 1s and everything else are 0s. So it's going to be k. But k is precisely, is k the rank of A? Yes, k has to be the rank of A. And the reason why is because, well, it's actually not obvious, right? Why is, okay, so we claim that this guy is true. So let's try to sort of demonstrate this claim. So we already have that E1 is given by the basis V1 to VKs. And we've even shown that rank of, or rather, we've shown that AVIs, the column space of A, is a subset of E1. So all we need to do is to show that E1 is a subset of the column space of A. So take any basis vector in V in E1, then AV1, well then V1, VIs are eigenvectors. Well, okay, so let's do it this way. Well, since VI belongs to the eigenspace with eigenvalue 1, means that AVI equals to VI. Well, but the right-hand side is simply an element of column space of A. So this actually tells us that if we take the linear combinations, the E1s will be a subset of column space A, and therefore the column space of A is equal to E1, which means that the rank of A, which is the dimension of the column space of A, is the dimension of E1, which simply, this guy is proven. The key insight really happens over here, and I couldn't do it without any assistance. So that was an interesting insight for this question. I gotta go for my dinner, and I will be back to record more linear algebra in just a moment. And now that I'm back from dinner, and by back from dinner I mean I had dinner and I went home and I had a long chat with my friends. It's a good chat. Slept, woke up, had brunch, and it's now in the afternoon. Let's come back to do more linear algebra problems. So these are the problems that tend to be a little more difficult, I think, as everybody knows. And we're going to struggle through it and see how we think about these problems. So the next question, actually was a question that appeared in my final. I still remember this very clearly. This is question 8. And we're going to let M and N be two n by n matrices. And have that V1 to Vn are linearly independent. Well, it's a set of linearly independent vectors. And they're not just vectors, but they're actually eigenvectors for M and N. So, under these special circumstances, the question requires us to show, and that's what we claim, that we can actually swap matrices around. Usually, we can't really swap matrices. Usually, it takes a bit of effort. In general, matrix multiplication does not lend itself to easily swap. And previously, there are some cases where we do, and sometimes the swapping can be a bit restrictive as well. So let's try and prove this. And how might I go about this? I'm thinking of a few strategies at the back of my mind, and part of me is wondering to myself, will these strategies work? I think I have a strategy that might be very sneaky. It is different from the first time I solved this, but I like this a lot. So once we have n linearly independent eigenvectors for M and N, that tells us that M and N are both diagonal. Well, not diagonal, yeah, diagonalizable. So since M and N are diagonalizable, there exist diagonal matrices such that P inverse AP equals to D1 and P inverse BP equals to D2. You might be wondering, wait a minute, what's P in our context? Because I just wrote this down, but I never wrote down P. Now, P is going to be the matrix whose columns are the eigenvectors. So P is going to be V1, V2, all the way to Vn. And the reason why we can write it this way is we may not know what are the eigenvectors, or the eigenvalues for each Vi. So in other words, we don't know. We know that AVI equals to lambda Vi, and we know, let's write it this way. We know that AVI equals to lambda IVI, and we know that BVI equals to mu IVI, but we don't know whether the lambda i's and mu i's are the same or not. And that's why the diagonal matrices, we have no idea whether they are the same. We could try to prove that they are the same, but it takes a bit of effort. But it's interesting because I'm starting to see a little sneaky trick that we could do here. And I think it shouldn't be A and B, it should be M and N. Quantities there. This should be M and this should be M and. And that's what it means for matrices to be diagonalizable. And what that tells me is that M can be written as P D1 P inverse. That's just by matrix multiplication. And N can be P D2 P inverse. That's by matrix multiplication as well. And then what we have here is that Mn will be the multiplication of these two matrices. But because matrix multiplication is associative, however you want to pronounce it, we can write this as P D1 bracket P inverse P D2 P inverse, and the P1s and P's will cancel out, and we're going to get P D1 D2 P inverse. And the beautiful thing about diagonal matrices is that we do know that diagonal matrices do commute. So in general, matrices don't commute, but when it's diagonal, we do get the commutative property, and we can literally go through the exact same process to show that this expression could be derived from unpacking the definition of M. maybe you might not be so convinced by this argument. Wait a minute, how do we know that two diagonal matrices can be swapped? Let's do a quick proof. Let's do a quick proof. Oh, what's this? What's one of it is called? That was awkward and embarrassing. Let's do a quick check. So we're gonna do a subclaim here. If D1 and D2 are diagonal, say n by n matrices, then we can swap them in terms of multiplication. So how are we gonna go about this? I'm gonna go ahead to try to prove this claim. Okay, right, proof. Let's prove great. Let's try to just do this, and again, this claim is going to help justify the swapping in this particular step. So let's write out, write D1 as D11, D12, D22, all the way to DNN. We'll write 2, well, it's a bit awkward. Maybe we will use C and D's instead rather than double D's. That way we can use the letter C to illustrate. So in this case, C, D, and C. Write C as the C's, and D's will be the D11, D22, all the way to DNN. And we can do a quick matrix multiplication to get CD will be, to do the multiplication, we're gonna take row multiplied by column, right? We take each item, so in other words, C1 times C11 times D11 plus zeros, plus these two multiplied by 0, these two multiplied by 0, and so forth. First term is going to be C11, D11. And the second row is going to be 0. Because when we multiply this term, if we multiply this row with this column, the first term is going to be 0 times something, that's 0. The second term is going to be something times 0, that's 0, and then we're going to multiply a bunch of zeros here on. So this term here is just 0. We can repeat the process, and we're going to get C2, 2, D2, 2, all the way to CNN, DNN. And we're going to get zeros everywhere else. We can represent it this way. Now, the beautiful thing about real numbers is that, or rational numbers, whichever you prefer, is that multiplication does swap in terms of real numbers and fractions, all that good stuff. So we can actually swap this to get D11, C11, D22, C22, so forth. Zeros. And finally, this actually does equate to DC. So that's a very short and quick proof as to why two diagonal matrices do. Essentially, it boils down to the fact that real numbers. And then that makes question 8. Alright. Now, question 9. For question 9, we will let V be the span of this set. And we have a bunch of information. We're given a bunch of information. We're given that for all the i's, Vi is a unit vector. And what that allows us to interpret is that the norm of Vi is 1, which means that the square of the norm of Vi is 1, and if we take the dot product of the Vi's. And what else do we have? Well, we also have that for I not equals to j, when we take the dot product this way, we're going to get a negative dot product. So that's interesting. I mean, we could try and interpret this geometrically as having an angle of more than 90 degrees, but that might not be so useful for us because we are not really working in 2 or 3 dimensions. We're working in a general number of dimensions. So in general, that might be a little bit the opposite. So the first question, the first claim is that no two vectors among these guys are linearly dependent. So no two vectors Vi in the set, which we're gonna call this S. Okay, we just abbreviate it just to be precise. No two vectors in S are linearly dependent. And it might be a little bit difficult to check every single pair of vector is not linearly dependent. So my approach would be to approach this by contradiction. Contradiction will help us start somewhere. And linear dependence has a nice property, right? You can write one vector into another. So here's my proof. Suppose otherwise, that means there are i's and j's where I is not equal to j, and this should already highlight the use. This condition should highlight the use here, and somehow we're going to use it fully. There exists some i's and j's such that they are linearly dependent, which means that you can write Vj equals to Cvi for some C in R. Of course, there is a technical definition, but you can basically reduce it to this situation. And that already raises the question, because that's where I really want to think about how to go about this. So then, what do we get? If we were to take the dot product on both sides, we get something pretty interesting, right? So let's work it out. Vj equals to Cvi. So we could take the dot product with respect to, we could take the dot product either J or Vi. I think because I want to simplify the right hand side, I might just dot it with Vi. Right? Because when we dot a Vi with itself, we can use the fact that Vi is a unit vector. The right hand side simplifies to C, and the left hand side is gonna simplify to Vj dot Vi. Since the i's and j's are distinct, we call this result star. By this result, the Vi dot Vj should be negative. So we will get C being negative. And this raises the question, how do I continue from here? So let's just take a look. So that gives us C being negative. Part of me thinks that there is another property that I could be using over here. Okay. So we have C being negative. Let's just take a look at what else can be done here. What is the question? The question is to show that we need to, in this setting, we want to try to obtain some contradiction. I think I have an idea. Let's consider the dot product with another vector and see. So, okay. However, for k not equals to I nor j, if we were to take the dot product of Vj with Vk, this term, C is negative. If we were to dot two vectors whose indices, in the sense, are not the same, then the dot product will be negative by star, right? So this will be negative by star. So on the right side, we're getting a negative times a negative, which is positive. But on the other hand, if we take Vj dot Vk, since the j's and the k's are not the same, it's going to be negative. This. And that tells us that, well, therefore 0 is bigger than 0. Projection. So the key trick I used here was the fact that if we just stay stuck with i's and j's, we might not really get anywhere. So we need to see what else. It turns out that we could actually use a different index and show that we can get a contradiction. So we've got a contradiction, and therefore the claim is true. No two vectors in S are linearly dependent. We might need to use this result, so I'm gonna copy and paste the entire question, and we're going to write at the side. So for question 9, right, part 2, this is after many takes. You can go check it out in the other video. We need to prove our claim is that the dimension of the subspace is bigger or equal to 3. Now we've already shown a few things. We've already shown that if V is equal to the span of V1 all the way to V4, such that all the VI's are unit vectors, meaning they have norm 1, and Vi.Vj is less than 0 for any I not equals to j, then no two vectors, no two VI's are linearly dependent. So we've already shown this result, and we now claim that the dimension of V is 3. So we're going to prove it, and after many attempts, here's the solution. What if the dimension is less than 3? Hopefully we get a contradiction, right? So suppose the dimension of V is actually less than 3. And without a lot of generality, we know that there will be at least two linearly independent vectors. Well, because if the dimension of V is 3, then V is equal to the span of V1 and V2, without loss of generality, because we can just do a bunch of relabeling, where v1 and v2 are linearly independent. That's going to happen. So we can write v3 as a linear combination of v1s and v2s, and v4 as a linear combination of v1s and v2s. And at this point in time, we just want to try to make use of as much information as we can. So the key idea here is to, well, let's do some dot products and hope for the best. So we'll take v3.v1 and v3.v2. What are we going to get? We're going to get c1 v1 plus c2 v2 dot v1. We can do the Raymo method for this. And these terms are going to be, well, this is going to be 1. So we can simplify this to c1 plus c2, well, v2 dot. And we can repeat the same thing for the bottom. Where the last equality follows because this guy equals 1. So we want to try to solve a bunch of things, and here's the fun fact about everything. The fun fact here, and of course our goal now is to eventually get a combination, right? The fun fact over here is we can actually interpret this as a system of equations, because we actually have the system of equations c1 plus some constant c2 equals to some constant, and some constant c1 plus c2 equals to a constant. I don't need to know what these constants are. I just need to know they're constants and they have some nice enough properties for us to use. And we could, in fact, just solve it directly without even bothering with Gaussian elimination. But let's just do Gaussian elimination because we can. So let's write this as a system of equations. This will be an augmented matrix. And let's do some row reduction. So we can take the second row and divide it. Well, we can take the second row and subtract it by v1.v2 times of the first row. That will get rid of the bottom left item, which is 0, and we will take 1 minus v1.v2 squared. That's true. 1 v1.2. I think I'm doing this right? I think I'm doing this right. Let's just add a bit more space here. We need a bit more space. v3.v1, in this case, v3.v2 minus v1.v2 of v3.v1. It is a little bit long, but it does get the job. Okay, and now what can we do here? Well, we have to be careful because we don't know whether this guy is going to be 0 or not. So we might need to do a bit of work. So let's suppose check. If v1.v2 is equal to, it's definitely negative, right? We know that, but let's write that down there. We know v1.v2 has to be negative, which means that the possibility is either it's equal to -1 or it's more than -1. So v1.v2 is more than equals to v1.v2 is more than equals to -1. And that tells us, well, it could be -1, it could be more. So, with two cases, let's consider two cases. If v1.v2 equals to -1, then we have a very peculiar situation over here. Then, we know that the modulus of v1.v2 is equal to 1, which is the product of the norms. And that tells us that v1 and v2 are linearly dependent. But that's a contradiction, because no two vectors be linearly. So we must have v1.v2 being bigger than -1 and smaller than 0, which means that this term here has to be strictly positive. That's the only way we can get that, and we can divide by this term. So now we can go back to our Gaussian elimination and divide by, take row 2 and divide by this term. We're going to get a very long expression which will actually get us very close to what we want. So this is going to be 1 v1.v2 0 1 v3.v1, and this entire numerator divided by the denominator. And finally, we just need to take the first row and subtract v1 times v2 of the second row. Now this looks absolutely atrocious. So let's give this a new name. Let's call this, say, t. And let's just write it this way. 1001 v3.v1 minus t. Leave it this way. Let's just give it a name because it's getting very hard to track all the symbols. So this tells us that c2 equals to t and c1 equals to v3.v1 minus t. And here's the beautiful part about this solution. Let me check, did I actually do this correctly? No, it's v1 times v2 of t. Only v1 times v2 of t. This is actually going to play an important role here. Here's the beautiful part of the solution. So t is going to be v3.v2 minus this guy divided by 1 minus this guy. I actually derived this in one of my previous attempts, but I didn't know how to use this. So this term is a product of two different vectors, so it's negative. Similarly, this guy is negative because v1.v2 is negative. This guy must be negative, and the product of two negative things is positive. So the whole numerator as an entirety is a negative minus a positive. That's negative. Now, on the other hand, we have derived that this term here is not just non-zero, it must be positive. Now, why is that such a crucial insight? It's because we get C2 being a negative over a positive, and therefore C2 is negative. In fact, C2 is your T, right? So T is actually your C2, but that means that C1 equals to v3.v1, which is negative, subtracted by a negative term times a negative term. So we're getting negative subtracted by negative, and that's actually going to be negative subtracted by positive, and the whole thing is going to be negative. So that's the crucial insight here. C2 and C1 are both negative. Now, why is that such a crucial insight? Well, if you got here, you probably are halfway there, but the last bit was the part I couldn't do. And when I saw the results, the solutions, this was an amazing piece of... We had v3 equals to c1 v1 plus c2 v2. And so the trick here is to multiply v3 with v4. Now, what I did in many of my attempts is to just go ahead and expand out the v4. But here's the trick. The trick is not to expand out the 4. Because v4 is going to be a different index from v1 and v2, we can get a negative sign from that. So here's the trick. This is the part which eluded me for the past, well, few hours. The right side is negative. The right side is negative. C1 we've shown is negative. C2 we've shown is negative. v1.v4, because they are cross term, is negative. This is v2.v4 is negative. So we're getting a positive plus a positive term. In other words, we're getting a negative term being equal to a positive term, which is contradiction. And that is how you solve question 9. This question eluded me. This question eluded. You can go and check out the full failed attempt in somewhere on this. It's there because I want to show you guys that I really tried a lot of ideas. I got somewhere, but not. So let's do the next question. Finally, let's move on. It's quite tiring, but it's what it is. So we'll let A, question 10, A be a square matrix of order n, and we will let Mij, right, be the n-1 times n-1 matrix obtained by deleting the ith row and jth column from A. So maybe an example. Here's an example. So if A is, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, then we'll say that M23, what is M23? It's going to be a 3 by 3 matrix, and the coordinate is going to be, well, this is the second row and the third. In the second row and the third column, we're going to delete these items, and M23 is going to be the matrix that remains. The symbol here is a little bit confusing. We call this the cofactor, but it is what it is. And we need to show this, right? We claim if A is invertible, then at least n of these matrices are invertible. Then at least n of the Mij's are invertible. So this is a very strong claim. We need to show that this is true, that at least these guys are true. It's really hard to work with at least because how many are there? But if you work with at most, you can probably take advantage of some properties from problem here. So here's my proof. Let's suppose, or contradiction, once again, you notice we're using contradiction basically every other proof. And that's so useful because it gives you weapons that a direct proof might not supply you with. Suppose for contradiction that there are at most n minus 1 of the Mij's are invertible. And what are we going to do? Well, I want to try to contradict A being invertible. And something about A being invertible is the fact that we know that A is invertible precisely when its determinant is non-zero. One of the most famous properties about invertible matrices. And how do we go about to establish that? That's the question. Well, let's try to calculate the determinant of A. So we know that at most n minus 1 of the Mij's are invertible. So how do we calculate the determinant of A? Okay, so let's calculate the determinant of A. And I'm actually going to use what we call the cofactor expansion of the determinant. So let's use the same example just to illustrate the point. I will prove using symbols, but the point remains. Let's just work with 4. We can generalize it to n. Now, the determinant of A can be calculated using what we call the cofactor expansion. And the cofactor expansion works this way. We will take one term here and multiply by the determinant of this guy. So now it's going to be A11 times the determinant, and we like to use either determinant or we could just use the 2 lines, but it's okay, we use determinant of what remains. And what remains actually is the cofactor matrix. So Mij's. Go to the next term, and instead of it being and we'll multiply, we'll add up the next term. So what do we know about this term? Well, firstly, we're gonna delete the remaining matrix will be formed from these guys. So in other words, it's gonna be A12 determinant of M12, and we will actually flip the signs each time. Change minus sign plus A13 determinant M13 and so forth, all the way to minus 1 to the power of n plus 1. What is it? N minus 1 plus 1 plus 1. Either's fine. Either's fine. Yeah, of determinant M1n. So how on earth does this help us prove what we need to prove? Well, this is where we need to try to invoke this special property. Now, there's no guarantee that from this calculation we will get determinant of A being 0 because, well, we are trying to contradict. So we're trying to contradict this thing. And we need to try to show that the determinant of A is, well, 0. It's not entirely obvious, but that's where we need to sort of try to make use of this assumption over here. How does that actually help us? Well, the idea is this. If there are at most n minus 1 Mij's are invertible, then we should have an entire row of Mij's that are not invertible. And the idea is this. If we the idea is that, well, let's think about it. How do we sort of argue the case? Well, if at most, say, 3 matrices, right, in our context for A over here are invertible, then we have a lot of matrices that are not invertible, right? In fact, if we think about it, each term here will produce a cofactor matrix. So each term gives you a cofactor matrix. So in fact, if we think about it, there are a total of, in the case for the n by n matrix, there are a total of n squared Mij's. If there are at most n minus 1 Mij's invertible, then there are at least, right, at least n squared minus n minus 1 Mj's that are invertible. Mij's invertible. They are not invertible. And the idea here is that, well, either your matrix is invertible or not. So if you have at most n minus 1 that are invertible, then the remaining will not be invertible and there are at least n squared minus n minus 1 of those. So what happens if we were to consider a row of matrices? Let's see what happens. So then n squared minus n minus 1 divided by n is going to be n minus 1 plus 1 over n, right? Sort of like there's a remainder term there. And this tells us that, if you divide it across n, and you have n minus 1 plus 1 over n, it's going to be bigger than n minus 1, right? It's going to be bigger than n minus 1. So what does that mean? That tells us there's going to be, I want to say that there is a row, there will exist some Aij, there will exist a row such that all of its cofactor matrices are 0. Are not invertible, right? So one row has n. Okay, so what is the result? There is a result of this. I think it's called a pigeonhole principle. So by the pigeonhole principle, at least one of the n rows, say row I, has n minus 1 plus 1 equals to n matrices that, cofactor matrices. In this case, we are using Mij's with that. Mij's that are not invertible. So, in other words, for this row, the determinant of each of these cofactor matrices. So here are all the different cofactor matrices in the row. Since they are all not invertible, the determinant must be 0. These matrices are not invertible, so the whole thing is going to be 0. So therefore, we're going to calculate the determinant of A not by taking the first row, where we don't know anything, but by taking the ith row. Say, determinant of A is going to be the AI1 determinant of Mi1 minus AI2 determinant of Mi2 all the way to minus 1 to the n plus 1 determinant of Min. And based on our analysis over here, all of these guys are 0. And if all of these guys are 0, the sum is going to be 0. But that tells us that the determinant of A is 0, which means that A is not invertible. But that's a contradiction. So it is a little sneaky. The pigeonhole principle here is pretty useful. So the idea is that because there's at most n minus 1 cofactor matrices that are not invertible, then the remaining if there's at most n minus 1 cofactor matrices that are invertible, the remaining cannot be invertible, and therefore you will have enough in a row so that when you take determinant cross that row, you get 0. Once you get 0, you show that the matrix is not invertible, which is our contradiction. That was better than the dot product question. That was awkward and embarrassing. Alright, let's keep going. Question 11. We will let A and B be n by n matrices, the same order, and they are square matrices. Our first claim, the null space of B is a subspace of the null space of AB. So that's our first claim. Now to prove this claim, I think it's not too bad because we can just show that every item in the left belongs to the right. So it suffices to show that the left is a subset of the right, because both items here, both null spaces are by definition vector space. So we don't have to worry about space or not. We just check the state relation. We're good to go. So we'll fix some item inside the left side, and our goal is to show that it lies inside the right side. We can decode our item here. So if x belongs to the null space of B, then Bx equals to 0. And if x belongs to the null space of AB, this means that ABx equals to 0. So we need to try to show this result. And I think it's not too difficult to see here that if we multiply by A on both sides, ABx matrix multiplication is associative. But by our hypothesis, Bx equals to 0. So we do get ABx equals to 0 and I can null space of AB. Now we have a second claim over here which says that the nullity of A plus the nullity of B is going to be bigger than or equal to the nullity of AB. And the moment I look at this, my brain immediately goes to rank-nullity theorem. One way or another, we're probably going to need to use that. How are we going to use that is not entirely obvious. I'm not saying it's easy, but I think we can try to use some information here. So the null space is a subspace of the null space of AB. So what that tells me is that, so let's do this. From the first claim, because the null space of B is smaller than the null space of AB, that tells me that nullity of B is going to be smaller than or equal to the nullity of AB. And this looks a bit concerning. How is this actually going to help us? The A is going to push us to where we need to be. But for now, let's just write it this way. The nullity of B by the rank-nullity theorem is n minus the rank of B. And the nullity of AB by the rank-nullity theorem is n minus the rank of AB. So we have this result. And obviously, well, not very obviously, this is going to be true. We're going to get this result here. So how do we make sense of this? Well, the rank of AB, okay, I'm trying to chart out a plan here. Well, we know, okay, here's the fun part. So yes, we could have gone this route, and that's not wrong. But we recall that the rank of AB is smaller than both the ranks of A as well, the ranks of A as well as the rank of B. So what we're going to get here is that rank of AB is smaller than this. So, well, this is awkward and embarrassing. Okay, we need to re-strategize here. Try that again. What do we want here? Let's just start here. Let's just start here and hopefully get to where we need to be. Okay, the nullity of AB, we want it to be smaller than the nullity of B and the nullity of A. Okay, let's try to write this as less than or equals to n minus the rank of AB. And we know that by the rank-nullity theorem applied to the matrix A, n is going to be equal to rank of A plus rank of nullity of A. It doesn't prove anything, apologies. I think there's something that I should be using here. I can't really put my finger on it, but let's try this. Okay, so we know that the rank of AB has to be smaller than the rank of A, which is going to be equals to, it's going to be n minus the nullity of A, which is not going to get us anywhere. Do this again. By claim 1, nullity of A will be nullity of B. It's going to be smaller than nullity of AB. What else has the question told us? Let's see what we used. We need to make a deduction. Okay, I think there's something that's really suspicious here. The nullity of AB should be smaller than the nullity of A and the nullity of B. There's something to this which seems really suspicious. I can't really pinpoint what it is. But there's something here. There is something here. And I'm not looking at the solutions. Not yet, hopefully. let's try some out. It says deduce. Well, rather we need to sort of use our first claim to solve this. So I need to find the upper bound on nullity of AB. And what if let's do that. Let's take n minus on both sides. So on the left side, by the rank-nullity theorem, we're gonna get rank B. On the right side, we're gonna get rank AB. This shouldn't be really too surprising for us. We've actually seen this a few times out in the rank-nullity theorem. I'm going to try to draw a picture and see what inside is here. So here's the null space of B. And here's null space AB. Part of me wants to link the null space of B with the column space of A, but I'm unsure on how to go about it. Try to do a visualization here. So we could go from one space via B to another space. We could end up at 0. And we could follow this up by A into the space, and of course the 0 will go to 0 here. And one thing is smaller than the other. One thing is smaller than the other. This is very suspicious. The nullity of A plus the nullity of B should be bigger than the nullity of B. So nullity of A is somewhat, in some vague sense, bigger. I think I have an idea. I have a little sneaky peek here. This might be a little bit dumb. This might be interesting. Let's read this. What does it mean for nullity of A to be bigger than nullity of B? It means that in some sense, when you add up the basis vectors in both null spaces, there are more basis vectors than the null spaces, than the basis vectors A plus B. So here's my idea. I sort of have an idea. So I'm going to try to show that a nullity of AB is either, okay, so here's my idea here. We'll take V inside the nullity of AB. I'm going to try to show that either V is in the what am I doing? In the null space of B, null space of AB. Either V is in the null space of B, or V is in the null space of A. I'm going to try that, and if I fail, you get to see me fail. So for the first case, if V is in the null space of B, then we're done. But suppose V is not in the null space of B, then BV by definition is non-zero. In fact, BV is going to be in the range, or rather in the column space of B and not in the null space of B. So what I'm thinking about in the back of my mind is something that looks a bit like this. Here's B, right? Or rather, here's your Rn, and then oh wait, what am I doing? Apologies there. BV is in the column space of B. Yeah, BV is in the column space of B. And then, well, since A of BV is equals to 0, is equal to ABV equals to 0, BV lies inside the null space of A. So maybe we'll do it this way. So either V is the null space of B, or let's say, or BV is the null space A. So that's what happened here. So what does that sort of mean here? If V is in the null space of AB, how does that affect the sort of null space of A? What does that mean here? I can't really derive anything actually. We're gonna have to try something else. So I claim 1, null space of B, the subset of null space of AB, which implies that nullity of B is smaller than or equal to nullity of AB. And we know that this is going to be, by rank-nullity theorem, these two things are equal to each other. Therefore, the rank AB is a subset of rank. Well, not rank of AB is a subset of rank of B, but rank of AB is smaller than the rank of B. Now, of course, we also know that rank of AB is smaller than. That's definitely going to happen as well. I think there's something we probably use here. Sorry, I think there is something that we might use here. If the null space of B is in the null space of A, does it tell us that the range of A lies inside the range of B? And then can we derive something about the null spaces as well? Not really. I mean, range and null space are pretty different objects. So we don't really have that feature. It's not entirely obvious. Nullity of A plus nullity of B is bigger than or equal to nullity of B. And A and B are square matrices of the same order. I think we'll need to use a basis vector argument. I don't think doing it this way is sort of helpful. I think we're gonna try. I think we can try this out. Try a basis vector argument. So what we'll do is this. We'll let V1 to Vk be a basis for the null space of A, and we'll let U1 to UL be a basis for the null space of B. I think we might get somewhere here. Now, from claim 1, we know that null space of B is a subspace of the null space of A. Of null space of AB. So that tells us that we can let U1 to UL and W1 all the way to say Wm be a basis for the null space of AB. And our idea here is to hopefully, so by claim 1, we've already put inside. So our goal hopefully is to show that this L plus M, which is the nullity, right? This is actually the nullity of AB, is smaller than or equals to L plus K. And this guy is going to be the nullity, this guy is going to be the nullity of B. And this guy is going to be the nullity of A. And what that means is that we need to show this goal, it's enough to show the goal that M is smaller than or equals to K. In other words, there are fewer vectors in the null space in the, this number is smaller than this number, right? The number of vectors there is smaller than the number of vectors the other side. And part of me wants to sort of do a basis argument, but I think rank might be even more useful here this time. I think we might get somewhere here. So what do I mean? So we know that rank of AB is going to be smaller than or equals to the rank of A. No, that's going to be true. And so the nullity, by rank-nullity theorem, this is going to be true by rank-nullity theorem. And we can write nullity of A is going to be smaller than nullity of AB, which means that we know that K is going to be smaller than L plus M. So that's going to be true. That's going to be true, but we want to show that M, if we were to get rid of the L, is going to actually be smaller than K. So we want to show, so this would give us some information about K and M, but it doesn't actually establish the result that we're looking for. We only know that M plus L is going to exceed K, but we don't know whether we will get that full information or not. And this might be interesting. Right? This might be interesting over here. So I'm trying to see how we can link the information over here. Because I think I have an idea. Here. We know that the AVIs are equal to 0, and we know that the ABWJs will all equal to 0, because the VIs belong to the null space of A, and the WJs are going to belong to the null space of AB. And I need to show that M is smaller than K. And we know that the BWJs cannot be 0 because these are other vectors outside of basis for null space of 2. We know that the BWJs are not 0. The BWJs equal to one another? That's an interesting question. I want to show that there are... Okay, so what I want to show is that from this we know that BW1 is going to lie inside the null space of A. That's going to happen. In fact, all the BWJs are going to be in the null space of A. So if we can show that these BWJs are linearly independent, then we know that the null space of A has at least M linearly independent eigenvectors, linearly independent vectors, and therefore K will be bigger than M. Here's the idea. If we can show that the BWJs are not equals to BWKs for J not equals to K, then there are, or rather, let's put it this way. If we can show that the set of BW1 all the way to BWMs is linearly independent, so there's a big if here, then we can show that the null space of A contains at least M linearly independent vectors. And that tells us, therefore, the basis has to be at least M. The size of the basis must be at least M. So this is our claim. This is actually our new claim here. We claim that this set is linearly independent. So let's try to prove this claim. I have no idea whether this will work. Let's start with the equation C1BW1 plus C2BW2 all the way to CMBWM equals 0. Then that tells us, okay, I think this is going to work. This guy will equal to 0, which means that this linear combination lies inside the null space of B. And if it lies inside the null space of B, then we can abbreviate this using the summation notation. Let's use the summations of the CIWIs. This will be equal to a sum of DJUJs for J equals to 1 to say L, because it belongs to the null space. And here's something I think we are good to go, because now we can write this as a linear combination of vectors. But the beautiful thing is that each of these wi's and uj's belong to this basis. Let me use that in a different color. In a different basis. Now that's cool, because if these guys all belong to the basis and we have a linear combination of them, they must be linearly independent, but the only way that's possible is if the ci's equals to the dj's equals to 0. But if the ci's equal to 0, then our set here is linearly independent. And we are good to go. Because once we've shown it as linearly independent, then the null space must contain at least m linearly independent vectors, which means that k is bigger than or equals to m. But if k is bigger than or equals to m, then, and I'm going to write this here just for emphasis, then k plus l is bigger than m plus l. But by our discussion just now, this is the nullity of AB, because these m plus l vectors come from these m plus l vectors. K is the nullity of A, and L is the nullity of B. And that is how we do it. That is how we use the information. It was struggling, and that's the part of the beautiful part of doing these questions live. Great. So clearly using the formula itself, it might not do us too much benefit, right? We actually had to go one step further to see what's happening. So question 12, we will let A be an n by n matrix. And for each R, we'll define the transformation this way, where we will send any vector u to the vector A u minus R u. So we are given a bunch more information. A is diagonalizable. And we're given that the eigenvalues of A are the lambda i's, right? So that it has eigenvalues lambda 1 all the way to k. We will now define the transformation as via t subscript r lambda 1 circle t subscript lambda 2 circle t subscript lambda k. This refers to linear transformation composition, right? This is going to be ours. And what do we need to prove? Let's prove that S is precisely the zero transformation. That might take a little bit of effort, but I noticed something about this transformation. The fact that we have eigenvalues is really sus, right? That actually should raise a few questions about the nature of the problem. So, well, let's just try to make use of that first. Now, since A is diagonalizable, the union of the k eigenspaces, the union will be precisely, well, not the union, but okay, so let's be more precise here. So since A is diagonalizable, let's first set up the problem properly. Now, for each lambda I, we will let we'll call this, say, what letter should we use here? I don't know what letter is good in this context. Let's use B. Let Bi denote the basis for E sub lambda I. Right? Bi for basis, I think that makes a lot of sense. Since A is diagonalizable, we know that the unions of the Bi's will form a basis for Rn. That's gonna happen, so it's all good. And we have that because of the fact that A is diagonalizable. A being diagonalizable is a very, very nice. Now, at this point in time, we don't know whether A is invertible, and in some sense, I don't think we need care, because S is defined using these T sub lambda i's. So my hunch is, okay, let's just try something out. So for any I and for any V inside, say B of I, if we take t sub lambda I of this vector, we're gonna get a vector minus lambda I vector. But if the vector belongs to the basis of the eigenspace with eigenvalue lambda I, then AV is gonna be equal to lambda IV, which is gonna be equal to 0. And the idea is sort of this property is gonna propagate throughout the transformation, correct? That's gonna be true for any v inside the VIs. So the idea is sort of it's gonna propagate through. Now, what that means, okay, so let's first sort of make a case here, right? So let's first start by doing this, right? Let's first start by making a case that we can actually do this propagation, right? So the idea is sort of, okay, here's our subclaim, if you would. If for any I and V in BI, we do get this property, then S is the zero transformation. And here's our quick proof as to why this works. The reason why we have a hunch that this is going to work is because for any vector u in Rn, since the B1s to BKs form a basis, right, and we can call this B, there exist vectors, say Vi, well, let's just say V1, V2, Vk, or Vn, inside B, such that U equals to a linear combination of these VIs, and Vi belongs to, well, not Vi, let's use J, then the Vj will belong to Bi for some I, right? So the idea here is sort of, we can write any vector as a sum of vectors with this special property. Now, why would that help us? It's because then what we have is if S of U is going to be S of the summation, and because a transformation S is linear, we can pull out the summation and the constants. I think we should actually put a brackets here. That looks more like it. And by our special property over there, this guy is going to be 0. So we do get S of U is going to be equal to 0. So all we need to do is to show that it's true for the vectors inside the basis. So the idea is sort of by answering the basis, we get every other vector for free, right? By solving the problem for V being in the basis, we can solve the problem for any other vector in Rn. That's why we make this claim. So that's a sort of a minor claim. Now we need to actually establish this claim. So now we claim for any I and V in Bi, S of V is going to be equal to 0. And here's a reminder that S is going to be equal to T lambda 1 circle T lambda 2 circle T lambda K. And here's also a reminder that T of R U is A U minus RU. And we've also seen just now that T of lambda I of V is going to be 0. So that's going to be sort of the little trick that we have up our sleeve, right? So let's attempt this question, and we're going to prove it this way, right? I believe in my previous attempt, I actually used a lemma to help me, but what we're going to do is we're just going to slowly make our way through, right? So we will suppose, right? Okay, so we'll take any, fix I inside, fix your I between 1 and n, between 1 and k, and V inside Vi. So we're going to show that S of V is equal to 0, so let's plug in S of V. S of V is going to be T lambda 1 circle T lambda 2 circle all the way to T lambda K, V is, right? So what is it going to be interpreted as? It's T lambda 1 of T lambda 2 of all the way to T lambda K of V. We close all of the brackets. Close the bracket, close bracket. Right, so that's the idea here. Now, if V is in lambda of K, we're good to go, right? It's going to be 0 if V is in, well, if V lies inside that particular basis. So in other words, this will be equal to 0 if V lies inside, if we chose, well, if V lies inside the basis of K. right? Because we have this property. If it's not, then we will need to do a bit of work. What kind of work do we need to do? Well, PR of u is equal to AU minus RU. Then, if we take TS of TR of u, we're going to get TS of all of that, which is going to be, since TS is linear, we can pull stuff out, or rather, we can pull stuff out like this. Because TS is linear. And what is TS? TS is going to be A times the input minus S times that same input. And maybe I should redo all of this. So let's sort of just dissect this TRU business over here. By our definition, TRU is AU minus RU. So what happens if we apply TS on both sides? Right, so in other words, what will happen here? We get TS of all of that. And what's TS of all of that? We know that TS is gonna be linear. But if we are doubting of that, don't worry. We can always just plug it in. Now, TS of all of that is basically going to be A of all of that minus S of all of that. Right? That's what TR of something means. That's what TS of something means. So it looks really, really messy, but we'll get there. Let's do a bit of algebra and let's clean things up a bit. A squared U minus RAU, because A is linear and therefore we can pull out constants, minus SAU plus RSU. And something interesting happens here. Because on the one hand over here we get TS circle TR of U. That's nothing more than function composition. And on the other hand, we can swap the S's and R's around. We can even swap the R's and S inside the real numbers because real numbers are commutative. And yet, this will be the corresponding calculation if we were to compute TR circle TSU. Now, what that tells us, and this is really important, is that TS circle TR will be equal to TR circle TS. This allows us to swap the terms. It allows us to swap the operators however we wish. Why is that useful? Because now we can do a bit of swapping. We can swap the operators around so that the last operator is T lambda I. I'm not saying that the T lambda K is not there. I'm just saying it's somewhere else and all we care about is T lambda I. And why do we care about that so much? Is because, say, T lambda something else. Lambda, say, J. I don't know what it is, but it is what it is. T lambda I V. I don't really care what that is. This property here, right? This property here allows us to swap the operators from here to here. And by function composition, we can decompose it this way. Something interesting happens because this item is 0. So we're going to get a linear transformation on 0. Just the whole thing is just like 0. And that's the solution. We've shown that SV is equal to 0. And since SV equals to 0, this means that we've shown that for any I, for any V inside this BI, SV of V will be 0. We've shown that if this is true, we will get the S being the 0 transformation, which is precisely what we're looking for. So that was the question, and that's how we sort of think about it. It does take a bit of effort, but it's okay. Let's keep going. Question 13. We have this thing. So A is going to be an n by n symmetric matrix. And we are going to try to prove that if there exists some m bigger than 0 with the property that am equals to I, then a squared equals to I. That's the question. So let's attempt to prove this claim. And how are we going to go about this? Here's the idea that I have at the back of my mind. We know that a squared equals to I precisely when a squared v equals to v, right? That's going to happen. So we want to try to show that result. And how do we go about that result? Well, we're going to do this. We're going to fix, this will be true for any vector v. So we're going to fix any vector v And we're going to make the observation that AMV equals to V, right? AMV equals to V because AM is I. And I think here we found we are stuck, right? And we are stuck because we don't really know what to do here. Well, we actually have a trick up our sleeves here. We have the fact that A is a n by n symmetric matrix. And whenever we see symmetric matrix, alarm bell should ring. There's always a very useful tool every time we see a symmetric matrix. And that is the fact that since A is symmetric, it is orthogonally diagonalizable. And if it is orthogonally diagonalizable, then there exists an orthonormal basis for Rn. And I think once we can establish this, we're good to go. So, just like before, every time we have this kind of basis property, I want to claim something that's a little bit, just like the previous question. I want to claim that if we can show that for any of the i's, a squared vi equals to vi, then for any vector, a squared v equals v. I want to show this, and the proof once again goes back to the basis proof, right? So we'll fix v in Rn. So in other words, I want to reduce the problem to just solving on the basis, then I get everything else. That's the idea of a basis. It sort of helps you strip away anything else. It goes to the heart of it. So fix v in Rn, then there exists unique constants C1 all the way to Cn, such that v will be a sum of the Ci vi's, right? From I equals to 1 to n. The trick is simple. Apply a squared on both sides. And since a squared is a linear transformation, we can pull out the sum and the constants. Not new stuff if you think about it. We've seen this trick many times. And if we assume that a squared vi is vi, then the a squared vi's will all simplify to vi. And once we get that, that's just basically v, and we're good to go. So we are now going to just simply prove the result for the eigenvectors. So now suffices to show that a squared vi equals to vi, where vi is in the orthonormal basis. But because vi is not just an orthonormal basis, it's an orthonormal basis of eigenvectors, right? These are actually eigenvectors. It's not just a basis. These are actually eigenvectors. It's very powerful. It's very powerful. Because we have this property of the eigenvectors, we can say, well, let a vi equals to lambda I vi for some lambda I. Well, because we know that vi's are eigenvectors. But we can raise it to the m power, right? So we can do this m times. And basically we're gonna do this, right? If we multiply it m times, it's basically multiplying, well, let's just do it slowly. Then a squared vi is gonna be a of a vi, which is equal to a of lambda I vi. Since a is linear, we can pull out the lambda I. And a vi is actually going to be lambda I vi and lambda I squared vi. And you can prove this inductively, and we can even obtain that am vi is equal to lambda m vi. The entire process just itself. And the beautiful part over here is that since am vi equals, well, since am is equal to the identity matrix, lambda m vi equals to am vi is just equals to vi. But if lambda m vi equals to vi, then vi is not zero because it's an eigenvector. This tells us that lambda of m, lambda to the power of m, must be 1. And this tells us that lambda must be either 1 if m is an even number, or negative 1. If m is an odd number, then, or rather, if m is an odd number, then lambda must be 1. If m is an even number, we might get minus 1. The beautiful thing is that we don't have to care because the lambda I squared is still equals to 1. But if lambda I squared equals to 1, then wait a minute, a squared vi is lambda squared vi, right? So therefore, a squared vi equals to lambda I squared vi is just 1 times vi. And isn't this basically the result that we were trying to prove? And we are done. So reducing it to the basis is a very useful trick. The fact that you have a symmetric matrix gives you a lot of information. You get eigenvectors that are orthonormal to one another. Really powerful over there. It's really cool. Alright, so let's look at the next question. This is question 14. And we have x and y square matrices of order n to n. We are going to make a bunch of claims. The first claim is that we get this matrix equals to 0 precisely when this equals to 0. And we're going to get a second claim that this matrix equals to 0 precisely when, well, sorry, apologies. Well, it's true. It's true. Yeah, precisely when x, y is equal to 0. So we're going to prove these two claims, and I think you could use the same technique for both, or you could use one claim to prove the other. So we're going to prove the first claim. And when I think of a transpose and the original guy, two things come to my mind. Either I think of least square solutions, or I would think about dot products, because if you recall correctly, we can think about dot products as the matrix transpose times the original matrix. And here's a very important part of dot products is that when we equal to 0, the only way it's possible is if the original guy is 0. So that's these are sort of the patterns I'm seeing right away even before I solve the problem. And this is probably going to help me solve it. I think we can all agree that if we go this way, if x equals to 0, then any matrix multiplied by x will be 0. So that's pretty straightforward, it's clear. Similarly for the second claim, if xy is 0, then x transpose times xy is x transpose times 0, and that's just 0, and this guy is clear as well. So, what's the proof of claim 1 in our instance here? The proof of claim 1, we need to try to show our goal to show that x transpose x equals to 0 implies x equals to 0. So, if I were to try to prove this right away, it might not be so obvious because these are matrices, these are not just numbers, these are not just vectors. And we could try and just expand out and hope for the best, but I like to think of matrices as linear transformations. That's a very powerful technique that we should be able to use just because it makes life so much easier. Yeah, it will make life easier. You don't have to do too many tedious calculations and it's gonna be fine. So I'm not interpreting this as a matrix equals to 0. I'm going to interpret this to mean x transpose xv equals to 0 for any vector implies that xv equals to 0 for any vector. So I'm going to interpret the matrices as transformations, and I want to show that if the x transpose x transformation is 0, then the x transformation must be 0. Once I rephrase the problem this way, I think you can see where I'm going with this. The reason why is because, let's just a way to prove it. So we'll fix v in Rn. Suppose xt xv equals to 0. You might be able to see very quickly that we can almost get this expression. But it does involve a subtle trick that you may or may not have seen before, and that's the fact that we're going to multiply by v transpose. Why do we multiply by v transpose? Because you recall that we can take the transpose this way, and this property is going to simplify to xv transpose xv equals to 0. And once we have xv transpose xv equals 0, by our, I guess you call it non-degeneracy property, if you would, not important, you're going to get xv equals to 0, which is precisely what I wanted to prove anyway. That's quite. Right? So that is that. So that's the first observation. Now, the second observation is even sneakier. Right? It's actually going to be even sneakier. Not the second observation, but the second claim. It's going to be even sneakier. We could actually use the exact same, and it's actually not going too long. Right, let's just write our goal first. Our goal is that x transpose xy equals to 0 implies that xy equals to 0. Again, one of the directions is pretty straightforward. And here's how I'm going to prove it. Right? I'm not even going to try to prove everything from scratch. I'm going to recall something very interesting about matrix multiplication. Here's our proof. So suppose x transpose xy equals 0. What we can do here is actually write y as a column of vectors. Okay, we'll just say size n for sake of discussion. We can write it as column vectors, and so we can write this as x transpose x y1, y2, all the way to yn equals to 0. And what we can do here is actually multiply the matrix in, right? We can actually take this guy, multiply it into the matrix involving the y's. So we're going to get x transpose x y1, x transpose x y2, all the way to x transpose x yn equals to the 0 matrix, which is a column of zeros. And I think you can see where I'm going with this. And where I'm going with this is the fact that we can actually use the result from before, right? Can you use the result before? Since each of the columns are zeros, xt, xyi equals to 0 for all i's. And we've seen from this argument that if the x transpose x of a vector is 0, then we must get xyi equals to 0. But once again, we can write this as xy1, xy2, all the way to xyn equals to the 0 columns, because each of the xyi's are 0, so each column will be 0. But on the left side, we can factorize out x. On the right side, we get a 0 matrix. And finally, these yi's, just like before, constitute the matrix y. And that's our answer. So that's how we can prove it. I believe if you prove it using the transpose trick, that will be perfectly fine as well. Alright, we're almost there. We're left with 7 more questions. It's not as short as I hoped. I thought it's going to be pretty quick, and as well, it's not as quick. So we'll let A be an n by n matrix, and we are going to suppose we're given Ax equals to B is consistent for any constant vector B. We want to show something. We claim that A transpose Y equals to 0 has only a trivial solution. So what do we need to show? Well, just the idea. Let's try to unpack this. We're going to show that if A transpose Y is equal to 0, then we automatically get Y equals to 0. Now, the other direction is pretty obvious, right? But it's this direction which is not as straightforward. So the fact that we have a y equals to 0 there makes me really suspicious, because if I can show, here's my idea here. So the idea. How do I show that y is equal to 0? There are a few ways, but one of the cleanest tricks we have up our sleeves is the fact that we can show that y transpose y is 0. And when we see it like this, alarm bells should ring, because once we get that, we might be good to go. But at the same time, it's not entirely obvious how we should go about it, because we don't actually have y's, we have A transpose. So this is not entirely obvious how we should go about in solving this, but this is where we need to think a little bit about what's going on. So A is an n by n matrix, right? So let's sort of visualize it like this. So Ax equals to B. Okay, write it as a m by n matrix multiplied by a n by 1 matrix. This is going to be an n by 1 matrix, right? It's going to be n by 1. You're going to get a n by 1 matrix. Okay, this will be very... Let me try that again. So Ax equals to B can be written this way. n by n times n by 1 to give you n by 1. So B is Rm and A is n by matrix. So how do we prove this? A transpose Y is slightly different, right? So A transpose Y equals to 0 is an n by m matrix multiplied by a n by 1 matrix to give you a n by 1 matrix. The last one's got zeros. You don't have to worry about that. So we notice that we'll let Y be, or rather, let's be a bit more relaxed. Suppose, actually let's do it. Suppose ATY equals to 0. But what is Y? Well, by our picture here, Y must belong to Rm. But if Y belongs to Rm, we have a result on Rm, right? We have a result on Rm. For any vector in Rm, this system is going to be consistent, which means it's going to have a solution. That tells me that, well, then there exists some vector u in Rn such that AU equals to Y. The reason being that AX equals to Y is consistent. So once AU equals to Y, we can substitute that into the equation, and this shouldn't be too new at this point in time. We've done a few questions of this nature just now. Actually, we've proven this result, right? Once we get this, we can go through the whole transpose trick and get the AU equals to. For the benefit of the doubt, let's do it one more time. This gives us U transpose AU equals to 0. And why are we doing this trick again? Well, because if we take two vectors, say AB, and we transpose them, we're going to get B transpose A transpose. So that is basically AU transpose AU here. And when do we have a dot product equals to 0? Only when the vector itself equals to 0. But AU is actually equal to Y. And we're done. And that's it. It's one of those weird things like, oh, well, that's very convenient, right? So we'll take that. Alright, we are almost there. Okay, so let A and B be n by n matrices. And we need to prove a few things to claim. Right? So suppose there exists an invertible matrix P such that P inverse AP and P inverse BP are diagonal. So we claim, right? Our claim is that we can actually flip the two matrices. So that's actually quite a useful result for us. If we get this property, we can flip A, B, and B. So that's our first claim. I think that's the second part of this. So let's prove our first claim. Since P inverse AP and P inverse BP are diagonal, this guy is going to be diagonal 1 and diagonal 2, right? So we'll write it this way. And since we know that there's this diagonal property, then we're going to get A to be P D1 P inverse and B being P D2 P inverse. This tells us that AB is going to be equal to P D1 D2 P inverse and BA is going to be P D2 D1 P inverse. Wouldn't it be nice if D1 equals to D2? Well, not D1 equals to D2, but D1 D2 equals to D2 D1. If this is true, we'll be good to go. There was a question that I was doing just now that actually, what's this result? But let's just go ahead and sort of write it up properly. So suppose D1 is given by, say, lambda 1 all the way to lambda n's, and D2 is mu 1s all the way to mu n's. Then D1 D2 is going to be lambda 1 to lambda n multiplied by mu 1 n. If we do matrix multiplication, we're going to go row by column. So we're going to get lambda 1 times mu 1 plus 0 plus zeros plus zeros. And the first term at the top is going to be lambda 1 mu 1. For the second row, we're going to get this row times this column. We're going to get 0 plus 0. And everything else is going to be zeros. So the second term is going to be 0. In fact, the only terms we're going to get are the diagonal terms. And go. The beautiful thing about the diagonal terms here is that these are just real numbers. And real numbers are somewhat nice in that we can flip the order. But if we flip the order and go through the calculations, we're going to get 2. So this is true, and this is true, and that is how we prove claim. Let's prove our second claim. Once again, A and B are n by n matrices. So we claim we're given, okay, let's just write it this way. We're going to suppose this thing, we're given that A has n distinct eigenvalues. Right? and we are going to make a claim. Every eigenvector of A is an eigenvector of B precisely when AB equals to A. So that is our claim. Now, usually to prove commutativity of matrices, it's not easy as you can tell. So I'm actually going to start by proving this direction. We're going to assume that the ABs and BIs work out nicely, and then we'll hope that things work out for us. So what we need to do is to show that our goal, well, let's fix an eigenvector V of A, and our goal is to show that V is an eigenvector of. So let's go ahead and try to prove this goal. So if V is an eigenvector of A, then AV equals to lambda V for some eigenvalue lambda. That's what it means. That's what it means. So how do we go about this? I think here is the... I think we're going to try it this way. Then let's multiply B on both sides, and let's just... Okay, so B, we multiply on both sides. We can simplify the right side by pulling out the constant because lambda, because B is linear. And then we can pull out the A, or rather we can swap the A and the B as follows. This actually tells us that BV is an eigenvector, of A with eigenvalue lambda. Okay, how is this supposed to help us? Well, here's the trick, right? Because A has n distinct eigenvalues. This is a very strict statement. It's not just a matter of diagonalization. It has n distinct eigenvalues. That means each eigenvalue, lambda, has eigenspace, as associated eigenspace, E lambda, whose dimension is 1. In other words, every eigenspace can only be sort of created by one particular vector. Since BV is an eigenvector of A with eigenvalue lambda, BV lies inside the eigenspace with eigenvector lambda. But we've already fixed this vector V to be the eigenvector in the eigenspace, and since you can only have one vector generating it, this guy must be the span of V. This must be the span of V. But what does that mean if it's in the span of V? That means there exists some constant, some real constant, such that BV equals to CV. Right? In fact, I'm going to go ahead and call this mu, because this condition here, what does it mean? It simply means that V is an eigenvector of B. With eigenvalue mu. That's pretty sick. So we used the n distinct eigenvalues here. If we don't know if it's n distinct eigenvalues, this is not a guarantee. We have no idea if it's true. Because we have A having n distinct eigenvalues, each eigenspace can only have dimension 1. That is how we can prove that V is an eigenvector of B. Next question. So now we need to show that if every eigenvector of A is an eigenvector of B, then AB equals to A. I think we solved this just now. Because if that's the case, right? So suppose every eigenvector of A is an eigenvector of B, then there exists an invertible matrix P. Well, that means that A is diagonalizable, B is diagonalizable, right? So maybe let's phrase it properly here. So here's how I think about it. I suppose we have every eigenvector of A is an eigenvector of B. Then, since A has n distinct eigenvalues, it has n distinct eigenvectors, then the n eigenvectors of A are the n eigenvectors of B. But if you have the same eigenvectors, and that means B has n eigenvectors, therefore A and B are both diagonalizable. And furthermore, there exists an invertible matrix and the same invertible matrix P such that P inverse AP and P inverse BP is diagonal. Oops. We've shown in the earlier claim, in the first part, this must imply that you can do commutativity of matrix multiplication. So that was cleaner. I thought that would have been longer, but okay, that was interesting. Alright. Question 17. We let A be an n by n matrix with the property that A squared equals to I. And we claim that the rank of I plus A plus the rank of I minus A equals to n. Alright, so this is our claim and we need to try to prove this claim. Now, of course, right off the bat, even without any thought, I would already consider the rank-nullity theorem. So I might think of it in those terms, right? But let's do a little bit of work here. I think there will be a bit of things to do. So let's first simplify this guy. And we can simplify it this way. I minus A squared equals to 0. Usually we can't really factorize because identity matrices are really nice. We can factorize it this way. And of course you can check. You can actually expand this factorization and you will get I minus squared. Now this should ring alarm bells because this looks a lot like the I plus A and I minus A in our claim, right? This looks a lot like it. So the real question is, what can we do for this? Well, one thing is for sure is that this is actually not entirely obvious, right? How do we actually go about this? The rank of I plus A. The rank of I plus A. I don't want to create a basis if I don't need to, but I might need to. If I want to. Alright, I think I see. So, here's the thing. If this I plus A, I minus A is equal to 0, then for any vector I plus A, I minus A times this vector must be the 0 vector. So in other words, I'm thinking in terms of vectors, but this helps me phrase things in terms of column spaces. What it tells me now is that for any U, because if you think about it, any vector of this form belongs to the column space of A, right? Of I minus A. It is going to belong to the column space of I minus A. So any U inside the column space of I minus A, right? U is equal to I minus A W for some W in Rn, which means that I plus A U is equal to I plus A I minus A W. But we've already seen that this will give us 0. It will give us 0. And that means that I plus A times U is going to give us 0. That means that U must lie inside the null space of I plus A. And this whole argument basically tells me that the column space of I minus A is a subset of the null space of I plus A. That's what this part basically tells me. And what remains here? Okay, I think we have something interesting here. So we have that the column space of I minus A is this. So this tells us that the rank of I minus A will be not more than the nullity of I plus A. Right? And this actually gives us something interesting. Therefore, rank of I plus A plus rank of I minus A will be not more than the rank of I plus A plus the nullity of I plus A, which actually is equal to n by the rank-nullity theorem. But we're not done, right? Because obviously there's just like one part and we have to think about the other part of the result. What if we did not just show this result, or we even showed the reverse result? What if we managed to show the reverse? So in other words, what if, and this is my claim, the null space of I plus A is a subset of the column space of I minus A. I think this might work. This will be great. If we get this, we can even replace this with equals, right? So let's go. Take any vector V inside the null space of I plus A. And what does that tell us? It tells us that I plus A V equals to 0. And that's not great, but it does tell us that V plus AV equals to 0. And I think I know what to do here, right? Then this tells us that V equals to negative of AV, right? Okay. And what can we do here? It's going to be A of negative V. Okay. I don't think I got anything here. Column space of I minus A. So I need to show that it's equal to V minus something. Right? I need to show that it's I minus A times V of something. So let's try and see what we get. Okay. So I'm very curious to see if this works. Okay. Go. Show that V lies inside the column space of I minus A. What this means is that V equals to I minus A W for some W in Rn. Can we show this? Try. So here's the idea. All of this is just the idea. This idea. Let's see what can we get. Well, V is gonna be equal to this if it's true. If it's true. Then that tells us that I plus A V is gonna be equal to I minus A I plus A I minus A W, which means that 0 equals to I plus A I minus A W, and we are not gonna get anywhere. Well, this could be a problem unless we went the other direction. No, I think we went the other direction. That was fine. Let's do it a different strategy. Right, so V equals to I minus AW, that gives us W minus AW. And we're going to show that V plus AV, BW plus A of W minus AW is W plus AW minus A squared W. Right, that's what it means, right? That's AV. Oh no, we're missing a minus AW here. W minus AW is AW plus A of W minus AW. So then that basically gives us, well, quit. AW plus A squared W. These two things will cancel out. We're gonna get I squared minus A squared. I minus A squared W. Right, so that equals 0. Well, that's not very convenient. We're not really gonna get anywhere from this, are we? We want to find a vector such that this is true. So how on earth are we even gonna go about it? That's the question. And I think, let me think of something. I think we needed to show, okay, we have the null space property. So let's see if we can get something out of this. Then V is going to be A of, well, AV is going to be negative of. Now, part of me wants to use eigenvalues here. I don't know if that makes a lot of sense. What if we did this? Let's try to play around and see what we can get. So, let's try something. Let's try. I'm just gonna try this out. What happens if we take I minus A of, okay, or maybe of KV, but K will be something we're choosing. Right, so this is gonna be KV minus A KV equals to KV minus K of AV, but AV, right, is equal to minus V, right? So KV minus K, or rather minus K of minus V, right, is going to be, or going to be embarrassing, it's going to be 2KV. Okay, this looks rather promising actually, because now we can just basically ignore the case. Let's just take away the case, and let's just redo this entire argument. So let's try to consider this guy and see what happens. Right, let's see what happens. We're going to get V minus AV. And we've seen that AV is equal to negative V, so this will be V minus negative V. That's 2V. So I minus A of V is equal to 2V, correct? I minus A equals to 2V, but that tells us that, well, okay, let's write that again. I minus A, V equals to 2V, but we can divide by 2 on both sides and get V equals to I minus A of half of V. Now, why do we write it this way? Because now we're writing V as I minus A of some vector, which belongs to the column space of I minus A. So therefore, we've shown that for any item in the null space of I plus A, it must belong in the column space. So this tells us, therefore, the null space of I plus A is precisely the column space of I minus A. And what that tells us is that the nullity of I plus A is precisely the rank of I minus A, which means not only do we have inequality over here, we can make it even stricter. We can make it even stricter by giving equality. And now this guy, instead of it being an inequality, it's going to be equality, and we are done. And that was the idea. So the idea sort of, could we try to take advantage of the fact that it looks really similar? Can we try to take advantage of that so that we can get the column space and the null space to actually equal to one another? Turns out we can. We have to be a little bit tricky on how we do it, right? So that's how we do it. Now, of course, when we look at this green working at the bottom, it looks like just black magic right away. But you notice there was a bit of a thought process that led up to this. Okay, the next question, 18, was a question that I was struggling with when I first attempted it. So, say, there are no orthogonal matrices A and B with the property that A squared minus B squared equals to AB. So this is not. I struggled with this question. Okay, there was a very clever insight which I took a look at, but I'm going to attempt this again without looking at the solution throughout. So, here's our attempt. It's very hard to show that something doesn't exist, so it's easier to show that if it does exist. So suppose there exists AB orthogonal matrices such that A squared minus B squared equals AB. Now here's the really important aspect about orthogonal matrices, right? Since A and B are orthogonal, the inverse is precisely the transpose. And this holds too. And this is such a crucial definition because we have so many properties involving transposers and not as many properties involving inverses. So in particular, the key property, which I remember I was quite blown away by, is the fact that if we were to add up the inverse matrices, we're going to get A transpose plus B transpose. But A transpose plus B transpose can be written as A plus B all transpose, right? So that's kind of important because you can't really do that with inverses. You can do that with transposers. So that's sort of the key insight there, and we probably will need to use this one way or another in our result. So let's start off with the given equation. And we want to derive a contradiction for this equation. This looks horrible. Let's start out this way. I actually can't do that. I'm sorry. I was so tempted to do that with real numbers, but we can't really do it with matrices. We need to be very, very careful here. Matrices don't afford us that special property. But we can add the b squared on both sides. And we can factorize out the b on the right. We can't factorize it for the left, of course. Now, this is the part where I think we want to use our transpose properties. So let's transpose on both sides. Let's take transpose on both sides. Write it this way. Because we have a special property about transposers that we wrote down just now. Well, transposers and powers work really nicely. We can just swap them if we wish. And the transpose of a product is if you were to flip the product. So the P transpose A plus B transpose. Now, since A and B are orthogonal, we can write A transpose as A inverse, and we can write B transpose as B inverse because of the orthogonalness, because we have the fact that they are orthogonal, right? And A plus B transpose, we've seen we can write it this way through this really sneaky trick. But we can actually do that. And so we get A minus 2 is B inverse A inverse plus B negative 2. So at this point in time, it feels a bit, what's the point? Like, why would anyone really care about this information at this point in time? And I wouldn't blame anyone for questioning. But we could play the same game with another manipulation. So instead of considering a squared minus b squared equals to ab, in the first run, we isolated a squared. Now we're going to isolate b squared. And, well, this is not as convenient. Oh, it's actually not too bad. Because we did plus a inverse plus b inverse, but the logic works if it's minus. The logic works the same. Transposers are really nice formulas, right? So we can take transpose on both sides, just like before. And we can write it as b to b transpose to 2, b minus a transpose. And we can now replace all the transposers with inverses. B minus A transpose is going to give us B inverse minus A inverse. So we get B minus 2 equals to B inverse A inverse minus A minus 2. That was... Oh, I wanted to say that was useless, but it turns out it doesn't look as useless as it seems actually. If you look carefully at the two equations, they look the same, but they're actually not the same, right? They're actually really and I think we are good to go. So let's try to simplify these two guys. So from this equation, we can get B inverse A inverse equals to A minus 2 minus B minus 2. And from this equation, we can get B inverse A inverse equals to A minus 2 plus B minus 2. So we can try to combine these two statements and get something interesting. I think we are on the... we have something interesting lined up for us here. So if we take 1 plus 2, we are going to get B inverse A inverse equals to 2A minus 2. And if we take 1 minus 2, we're going to get B inverse A inverse equals to 2b minus 2. And what we're left with here is that these two will combine to give us A negative 2 equals to B negative 2. And we can take powers pretty easily. A must equal to B. And here's the catch. If A equals to B, then what's the original equation? The original equation states this, right? Then A squared minus B squared equals to AB. Right, this is what the equation gives us. But if A equals to B, the right side is gonna be, say, A squared, or just like B equals A. The left side is gonna be A squared minus A squared, which is 0. And if A squared equals to 0, then A is not... Well, if A squared equals to 0, that means A squared is not invertible. But A is orthogonal implies that A is invertible, which implies that A squared is invertible. And here we get a contradiction. So therefore, this statement must be false. And therefore, this statement is true. And we are done. Okay, we have 3 questions to go, but I'm going to take a short break and charge this Apple Pencil, and we'll be right back. Alright, we have 3 more questions to go, and we're good to go. So, question 18. Well, we've done question 18. What am I saying? Question 19. We'll let S be an orthonormal basis for the subspace V. We'll let A be an M by N matrix. And we'll define M to be this item here. It's going to be the sum of this thing. It's the sum of the norms of A of ui. Each a of ui, you take the norm, and then you sum them up. That's m. If you've ever done this, if you're interested in this area of math called functional analysis, there will be results similar to this. Yeah, that is it can get a little bit tricky. So let's go ahead and prove our claims. So let's prove our first claim. The first claim is that for any v, which you can write as a sum, a linear combination in v, right? We'll get that the norm of v is upper bounded by this term. So that's the first observation here, and we can try to prove it. In fact, the proof comes from this thing called the triangle inequality, right? So by the triangle inequality, the norm of v, which is the norm of the sum, the triangle inequality tells us that the norm of the sum will be upper bounded by the sum of the norms. I believe we call this a sub-additive function. Not sure what the terminology is, but I think there's a name for it. This allows us to pull out the ci's with the modular symbol. This is called homogeneity. And this guy looks a lot like this guy, with the exception being that the norm of ui is up there. But each ui is a unit vector because S is orthonormal, which means that we're good to go. That's our first claim. Our second claim is this, right? Suppose, furthermore, that norm of b is less than or equal to 1. Then each ci has to be smaller than or equals to 1. That is the claim, and I am not too sure how we're gonna go. I think this is fine, and the reason why is because vi is smaller than or equals to 1, then ci is also smaller than or equals to 1. I could try to show a contrapositive, but I don't think that's gonna work. Let's take a look at this for a moment. I think I have an idea on how to go about this. So the trick is to, instead of considering the norm, we're going to consider the dot product. Right, so here's how I might go about it. So to show that the norm, since the norm of v is smaller than or equals to 1, it tells us that the square of the norm is smaller than or equals to 1. But that tells me that the dot product is smaller than or equals to 1. And each v, since v is the linear combination of ci ui's, the dot product is going to be the dot product, well, let me write this down. So 1 is going to be bigger than the dot product of the v's, and the dot product of the v's is going to be the dot product of the sums. And when we do dot product of sums, we want to make sure that the indices don't really overlap so that we can account for all of the different possible cost terms above. So this will simplify to a double product this way. And the reason why we can do this, by the way, is because we have there are no I terms inside the summation of j's. So in other words, every term here involving sub-i's is not in here, so we can basically move it. This is an important result because this tells us that ui's and uj's interact in a very, very specific way. Orthonormal vectors have very specific properties, right? Because we know that ui.uj is either 0 or 1. Some people will use what we call the conical delta, okay? Not important. And it's 0 when I is not equals to j and 1 when I equals j. So because of this property, this is going to be 0. Right, we're going to consider all the j's. For each I, we're going to consider all the different j's. The ui.uj is going to be 0 if j is not equals to I. And it's going to be equal to 1 if j equals to I. So we write it here that for any fixed I, the summation from j equals to 1 to k of ci's j, ui, uj is going to be 0 if I is not equals to j. And it's going to be 1 if I equals to j, and 0 otherwise. So this whole thing, well, is 1 times ci squared, right? So you can get ci squared. And what this tells us is that this sum here is going to be equal to ci squared. The beautiful thing about ci squareds is that we can write each ci squared as the modulus of ci whole squared. And what this tells us is that if the sum of ci squareds is, well, if we have a sum of ci squared, it's gonna be bigger than, say, of course, m for any m from 1 to k. So what we have shown is that modulus of cm squared, after doing all that hard work, is less than or equal to 1. It tells us that mod of cm has to be smaller than 1. And that is our second claim. So let's just write down our claims that we have proven so far, because we might need to use them. First claim is that if we have, okay, so we have, let's write the setup before we write the claim. S is of O. Our first claim was that for V equals to the summation Ci V Ui's V, the norm of V is bounded above by the summation of the Ci's. That's our first claim. I don't know whether we need to use it or not, but it's a long question. So claim 2, for V equals to the summation, if the norm of V is smaller than 1, smaller than or equals to 1, then each of the coefficients, the absolute value must be smaller than 1. For our third claim, we need to show that for V, okay, so V in V, if the modulus of V is less than or equals to 1, then modulus of AV is equal to M. We need to prove this claim, so let's prove it. And I think this should be alright. I think this should be alright. Let me see. Well, this is a little tricky. How do I think about it? So, modulus of AV is going to be, by definition, the modulus of the A of the summation, which, since we have linearity, we can push everything inside. Okay, I think we're good to go. Right? We can apply the triangle inequality because the norm of the sum is bounded above by the sum of the norms. And we can even pull out constants from the norm. And at this point in time, it feels a bit questionable, but here's the trick, right? Because the norm of V is smaller or equals to 1, by claim 2, which we have proven, each of the Ci's is bounded above by 1. That means this whole thing is bounded above by the summation. Each Ci is bounded above by 1. So we're going to get bounded above by this way. And what we have here so far is that this guy is precisely our definition of M. Because if we recall correctly, M is the sum of the norms of the AUIs. So call that this guy is the sum of the norms of the AUIs. So that basically is our result over there for claim 3. Finally, for claim 4, if we were to relax the condition, so for any V in V, modulus, the norm of AV is bounded above by M times the norm of the norm of. And the proof of this claim is actually a really well-known trick in the functional analysis of linear algebra sphere of things. Here's the trick. Observe that V over the norm of V, if we take the length of this guy, right, this is gonna be the length of V over the length of V, which is 1. So we can basically apply claim 3. By claim 3, the norm of A times this vector, right, will be bounded above by M because of linear algebra. Let's just do some calculations here. A of 1 over norm of V, we can write it this way. We can pull out the constants twice, so we're getting 1 over norm of V, norm of AV. And finally, these two things we can summarize this result as 1 over norm of V, mod of AV, mod of M. Finally, null of AV on above by M V, and we are done. So these are one of those little tricks that you can use to prove if you wish. We're left with 2 questions to go, and I am looking forward. Let A be a square matrix of order n, and we have the property that rank of A plus rank of I minus A, A minus I, equals to n. And we've seen a few questions of this type before, right? We've seen a few where we need to check the range and column space, null space, all that. And we claim that A squared equals to A. That is our claim. And what do we need to do to prove this claim? So once again, it's very hard to work with matrices. It's a lot easier to think about them as transformations on vectors. So I'm thinking of this not as A squared equals to A, but as A squared minus A equals to 0 transformation. And because of the identity matrix, we can even factorize this. Now this is a little tricky. I'm not sure whether I want to factorize it this way or this way. I think I want to factorize it this way. This might be useful. So in order to show this claim, we need to prove that A minus I, AV equals 0 for any n. Now this itself is rather suggestive, because if that is the case, this looks a lot like a situation of some null space, column space business, right? If any v in Rn, any v is precisely an element in the column space A, we want to show that A minus I multiplied by each element in the column space. Let me write this way. This here is U, we call it U, will always lie inside column space of A. We want to show that A minus I acting on the column space of A gives you, right? So in other words, one very interesting trick here is to show the column space of A is a subset of the null space of A minus I. Now that being said, this might be possible, but it might be really hard as well. So sometimes I might think about it as A of A minus I equals 0. And therefore, by the same principle, column space A minus I is a subset of null space of A. I'm not sure which is easier to prove actually, right? So we're going to have to sort of do the hard work and hopefully hope for the best. So how do we start? Well, the equation is really suggestive, right? Because rank of A minus I is equal to n minus rank of A. And by the rank-nullity theorem, this is actually the nullity of A. So what we have here is the rank of A minus I equal to the nullity of A. Now that being said, we could have done rank of A being equal to nullity of A minus I. Since we are using this one, actually I want to use the other version. I want to use the other version. I think I remember there's some hacks that we can employ here. Let's do it this way instead. Right? We can do that, right? Because the equation is still the same, and rank-nullity theorem still works. So we have that. So what we need to show is one of these results. In fact, most likely we want to, since this is the rank of A, it's directly related to the column space A. We probably want to show this result. Right, here's the interesting bit. We are given the equality. We are given essentially that rank of A is the nullity of A minus I. And what that means for us is that the column space of A, being a subset of the null space of A minus I, coupled together with the equality in the dimensions, will allow us to conclude that these two guys must have the same dimension. In other words, if the column space is a subset of the null space, then it actually must equal to one another. But by the same logic, the null space of A minus I must be a subset of the column space of A. Because in order for the two spaces to be equal and them having the same dimension, it is equivalent to the null space being a subspace of the column space. And the reason why I formulated it this way is because it turns out that this is going to be the key to solve our question. Why do I say that? Well, we want to show this. This is our goal. Why is this our goal? We can show this, then we can show this result. We can show this result, then we get this, we get this, we follow the train of arguments to get what we're looking for. So that is what we need to show. So let's fix any item inside the null space of A minus I. And what that tells us, A minus I of that item equals. But if A minus I of the item equals to 0, then AX minus X equals to 0. But if AX minus X equals to 0, then X equals to AX. And why do we care about X being equal to AX? Because now X equals to A times something, and that means X belongs to the column space of A, which allows us to prove that the null space A minus I is a subset of the column space A. We needed to show that the column space is a subspace, actually. But because of all the equation they gave us, we can actually flip the problem, actually. We can actually flip the problem. And the flip problem is way easier to prove than the direct problem. The direct problem is, I had no idea how to proceed. I was like, yeah, there might be a way to go about it. I genuinely have no idea how to proceed. So, yeah, that's that. So there's that, and we're on to our final question of this linear algebra. Run through, walk through, whatever you want to call it, man. You should call this like linear algebra walkthrough. That's actually an interesting title, yeah, possibly. Let A be an invertible matrix. So let A be invertible. This might be important. Of order n, so it's on n by n. It has n distinct eigenvalues. Here we get this interesting property. In the previous question, we actually used this very crucially in one of the arguments, so we're probably going to use it again. But we're going to go through that again anyway. So you can check out the previous video, but or previous part of this. Now, suppose B is a square matrix with the property that AB is equal to BA inverse. This is a little tricky, right? It's BA inverse, not BA. So we don't even get a commutativity, we get this weird modified commutativity. Describe it, it's fine. And our claim that we want to prove is that B is diagonal. So, how do we start? Well, okay, let's start with the fact that A has n distinct eigenvalues. Alright, so let lambda 1, lambda n be the eigenvalues of A with eigenvectors b1, bn. And furthermore, we know that the lambda i's cannot be 0, and the reason why that's the case is because A is invertible. So that might come into play, but I'm not too sure what to do from here. We do know that these are eigenvectors, so we can play around with that and see what happens, right? So here's something interesting about eigenvectors, right? So if A is invertible, then A, so we can let fix Vi from these n eigenvectors, then AVI equals to lambda Vi lambda IVI, because VI's are eigenvectors, right? Then we can take the inverse. We can actually take the inverse on both sides. On the left, the inverses cancel out, so we just get Vi. On the right hand side, we can pull out the lambda i's because inverses are still in different formations. And then we get that 1 over lambda I Vi equals to A minus I minus 1 Vi. This is legitimate because the lambda i's are non-zero because A is invertible. So that's gonna be interesting for us because now we can do it this way. I noticed that we have A inverse of Vi, right? A inverse of Vi. We can put a B in front and try to play around with the properties. So B of A inverse Vi is gonna be B of 1 over lambda I Vi. We can pull the constant 1 over lambda I out. So 1 over lambda I BVI is going to be equal to BA inverse Vi. But by the assumption, BA inverse Vi is going to be ABVI. And this is something very interesting if you take a look here, because we actually get A of something equals to a constant times the same something. So that tells us that BVI is an eigenvector of A with eigenvalue 1 over lambda I. That's really interesting here. That's actually pretty useful. Because if it is an eigenvector, and we know that A has n distinct eigenvalues, we know it's going to be distinct, then the eigenspace the eigenspace of 1 over lambda I is spanned by just one vector. And what vector would that be? I feel like I might have messed this up somewhere. Okay. A lot of me thinks I messed up this proof somewhere. But let me sort of take a look. No, I think this is fine. BVI is an eigenvector of A with eigenvalue of that. So EI, okay, I think we can still do it. This still works. So the eigenspace associated with the eigenvalue 1 over lambda I can only be a single vector, right? It can only be a single vector. Let's call it U for some U in Rn. That tells us that BVI equals to CU for some C in R, right? That tells us that's the case. But once that tells us that's the case, then let's observe some stuff. Then ABVI equals to CAU, and ABVI we know is going to be equal to 1 over lambda BVI equals to CAU, and AU is an eigenvector with eigenvalue 1 over lambda. So this is going to be C times 1 over lambda I U. I think that gets us nowhere. Well, that was awkward and embarrassing. I think I have a better plan. Here. Well, if BVI is an eigenvector of A with this eigenvalue, then the eigenspace has to be spanned by BVI. There's only room for one distinct direction. So, let's check this out. Then, okay, wait, this feels a bit tricky. I'm gonna have to backtrack over here. See what happened. Did I mess this up? I feel like I've messed this up. Oh, we're not looking for B. What am I doing? The claim is not that B is diagonalizable. The claim is that B squared is diagonalizable. So, okay. We weren't even answering the question. Okay, so let's try that again. So we have B equals to this guy, which makes it equals to ABVI. Let's call this up. We can still just do this calculation, right? The question is not asking for B, it's asking for B squared. So let's apply B on both sides again and see what happens. Now on the left side, we're going to get 1 over lambda I B squared VI. So that's going to be our item of interest later on. On the right side, we get BABVI. This is not very promising because we know nothing about BA. Oh wait, but I think we can play around here. So right here, we can multiply by A on both sides because A is invertible. Yes, okay, great. So we can start from this, start from this equation. And we can multiply by A on both sides because A is invertible. Great. This simplifies, the right-hand side simplifies to B. And we can multiply by A inverse on the left because once again, A is invertible. And the left-hand side will simplify to BA. Alright, great. Now we can do some replacements and that's gonna be very good. So, we can now replace the BA over here with an A inverse B. And then we have a BVI, which gives us A inverse of B squared VI. And we are good to go. Now we have all the tools we need. The reason why is because B squared VI is an eigenvector of A inverse with eigenvalue 1 over lambda I. And what this corresponds to is that B squared VI is an eigenvector of A with eigenvalue lambda I. It's actually the same eigenvector. It's quite an interesting property there. And what that tells us is that since A has n distinct eigenvalues, the eigenspace is ease of lambda I equals to the span of VI, which tells us that B squared VI lies inside the span of Vi. But if b squared Vi lies inside the span of Vi, that means there exists some constant c such that b squared Vi is equal to Cvi. And what does that tell us? That tells us that Vi is an eigenvector of B. That's really good because we have n distinct eigenvectors from A, right? So therefore, since A has n distinct eigenvectors, right, which are eigenvectors of B squared has n distinct eigenvectors. And once b squared has n distinct eigenvectors, we can conclude that b squared is diagonalizable. And we are done. And that's all of the linear algebra questions we have today. If you want to check out some other linear algebra, you can click on the video on the screen somewhere, somehow. Not too sure where, but enjoy yourself.